Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the strangest and most beautiful ideas in all of science, that reality itself might wait for us to notice it before deciding what it truly is. But before we open that door, I'd love for you to take a moment to like this video and subscribe, only if you truly find these gentle explorations soothing. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a quiet joy to imagine our little constellation of curious minds, each in our own small corner of time. Now feel free to dim the lights, let the hum of a fan or the rhythm of your own breathing keep you company, and allow the day to drift softly out of focus. You don't have to think or even follow too closely. Just let the ideas wash gently over you. Tonight we'll open the box that holds not just matter, but mystery itself, and see how even the smallest things can teach us the calmest truths. Imagine a small wooden box sitting on a table in front of you. It doesn't look remarkable. Smooth sides, no markings, just a lid and a quiet presence. You're told that this box can create anything you wish for. You can ask it for an apple, a key, or a shimmering feather, and somehow it can provide all of them at once. The trick, though, is that it doesn't choose which one to become until you lift the lid. Before you look, every possibility lives together inside, as if the box is waiting for your gaze to decide which story to tell. This little box is a gentle doorway into the idea of quantum superposition. In the smallest realm of reality, smaller than atoms, smaller than the dust that dances in moonlight, the universe behaves as if every possible version of something exists at once. A single electron can be here, there, or in 1,000 other maybes, all at the same time. Only when we measure it, when we peek into the box, does it settle down and say, "I am here." Physicists call that quiet act of choosing the collapse of the wave function, but that sounds colder than it feels. You can think of it instead as a soft decision, a moment when the universe finally picks one of its countless possibilities. It's not an explosion or a dramatic event. It's more like fog solidifying when touched by morning light, or a thought becoming clear just as you wake. For a long time, people imagined the universe as a clockwork, every gear turning in precise, predictable motion. If you knew all the gears, you could know every outcome, past, present, and future. But quantum mechanics whispered a different kind of truth, that at the deepest level nature keeps her options open. Even the act of looking, of observing, seems to play a role in how things turn out. It's not that we create reality by watching it, but that the very act of interaction changes what's possible. Think of a soap bubble. It's perfect and round until you touch it. Then it wobbles, glimmers, and sometimes bursts. In the same way, measuring a quantum system isn't like reading a label on a jar. It's like touching the bubble. You can't learn about it without changing it just a little. That's what makes quantum physics so delicate, so hauntingly beautiful. It treats knowledge itself as something that leaves fingerprints. This strangeness isn't new to humanity. The ancient Greeks once believed the world was built from 4 simple ingredients: air, fire, water, and earth. That was their way of explaining all the wonders they saw. Today we've replaced those 4 elements with something even more mysterious: fields, particles, and probabilities. But the feeling, that mix of curiosity and unease, is still the same. And maybe that's why quantum mechanics scares scientists a little, even now. Not because it's dark or dangerous, but because it's humbling. It reminds us that the closer we look at the fabric of existence, the less certain we can be about what we'll find. The universe isn't a stage with fixed props. It's a living script, rewritten every time something interacts with it. So as you listen, try to imagine the world not as a solid, finished thing, but as a shimmering field of possibilities, always in motion, always halfway between becoming and being. Reality, it turns out, isn't carved in stone. It's more like a whisper waiting for someone to listen. And as we drift further into the story, we'll follow that whisper back through time, from the first thinkers who guessed at the world's ingredients to the quiet revolutions that revealed the tiny, trembling architecture beneath it all. Our journey now turns toward the ancient dream of matter itself, and how it slowly began to dissolve into mystery. Long before anyone spoke of atoms, electrons, or fields, people looked around at the world and tried to find patterns that made sense. They watched fire flicker and vanish, water flow and freeze, air disappear yet carry the scent of rain, and soil turn to dust and back to green again. To them, the world seemed built from 4 eternal ingredients: earth, air, fire, and water. It was a comforting thought, simple, balanced, and human. Everything we saw could be blended from those ancient elements, like pigments on a cosmic painter's palette. But the universe, as it turns out, is not so easily contained. When science began to look closer, far closer, those elements gave way to new foundations. What had once been air became a collection of invisible particles, moving so quickly they made the wind. What had been fire became the shimmer of atoms exchanging energy. Even the solid earth beneath our feet was no longer solid when seen through the lens of physics, but mostly empty space with tiny charges dancing within it. Imagine, if you will, that every grain of sand, every leaf, every drop of water is made not of smooth stone or soft tissue, but of tiny systems, miniature worlds bound by invisible laws. For centuries, philosophers dreamed of these indivisible atoms. It was a poetic guess that would eventually turn into one of the most powerful discoveries in history. When scientists finally peered deep enough to see the atom's secrets, they found a structure far stranger than anyone had imagined. At the heart of each atom lies a tiny nucleus, a cluster of protons and neutrons packed together so tightly that if the atom were enlarged to the size of a cathedral, that nucleus would be smaller than a single grain of rice at the centre. Around it, electrons whirl in invisible clouds, never fixed, never still. They do not trace neat circles like planets around a star as we once thought. Instead, they blur into a haze of possibility, a shimmering fog of maybe here and maybe there. Every element, every metal, every breath you take is defined by just one thing: the number of protons in that nucleus. Hydrogen has 1, helium has 2, carbon has 6, and so it goes. Change that number and you change the very nature of the world. Water turns to metal, air to rock, colour to light. The entire variety of the visible universe comes from this simple arithmetic of protons. And yet, even this order conceals deeper wonder. Inside those protons and neutrons are smaller particles still, quarks, bound together by the strongest known force in the universe. Around them, neutrinos stream through everything, passing through your body in endless waves, silent and unseen. They are ghosts of creation, messengers from the Big Bang still whispering across time. If all this sounds overwhelming, it helps to picture the atom as a kind of musical instrument. Each particle plays a note, vibrating in harmony with others. When you strike a key on a piano, it sets the strings inside quivering, and those vibrations fill the room with sound. The atom does something similar. Each electron hums with a certain frequency, its energy level, and when it moves from one state to another, it gives off light. The colour of that light tells us exactly what kind of atom it came from. That's why sodium glows orange, hydrogen glows red, and neon burns with a soft pink flare. Every element sings its own song, a quiet symphony of quanta echoing through space. The great leap came when scientists began to realise that these patterns, the colours, the charges, the forces, couldn't be explained by classical physics alone. The old rules of cause and effect worked beautifully for falling apples and orbiting moons, but they fell apart when confronted with the atom's secret rhythms. At this smaller scale, particles refused to behave like solid marbles. Sometimes they moved like waves, spreading and overlapping. Sometimes they struck like sparks. Sometimes, impossibly, they did both. Max Planck, a German physicist with a fondness for the meticulous, discovered that light doesn't flow smoothly like water from a tap. It comes in tiny packets, quanta, as if nature blinks between notes instead of sliding across them. That single realization changed everything. It meant that the universe at its core is not continuous, but pixelated, made of discrete steps of energy, like the soft ticking of a hidden clock. Albert Einstein followed, showing that light could act as a particle too, one that could nudge electrons free from metal surfaces, an idea so radical it would one day earn him the Nobel Prize. Then came Niels Bohr, who painted the atom not as a miniature solar system, but as a place where probability ruled. The electron didn't orbit the nucleus. It existed in a cloud of possibilities until measured. The world, he said, was not simply what it looked like, but what it could be. This was the dawn of quantum mechanics, a new language for describing the invisible. It told us that nature is built not from solid things, but from relationships, from chances and changes. It said that every particle in the universe carries within it a spectrum of possibilities, and that observation, the act of interacting, is what gives it shape. For a while, the new theory felt almost blasphemous to the classical mind. It suggested that the universe wasn't a perfect clock after all, but a shimmering web of maybe. Yet, it worked. With this strange, abstract mathematics, physicists could predict the colour of stars, the behaviour of materials, even the chemistry of life itself with astonishing precision. If this feels abstract, think of it this way. The same rule that governs an electron's leap around an atom is the rule that lets your body glow faintly in infrared light, that lets the stars sparkle, and that allows every signal in your phone to move as pulses of energy instead of continuous waves. The quantum world isn't far away. It is here, humming beneath your heartbeat. So as you lie there, listening, imagine peeling back the world layer by layer, from the air that cools your skin, to the atoms in your pillow, to the particles inside those atoms. Imagine seeing them dance, jittering, leaping, entangled, vanishing, returning. Each one is following the same mysterious rules quietly and faithfully without pause. And as we follow the thread a little further, we'll leave the comfort of atoms behind and drift into something stranger still. The realization that beneath these particles lies a deeper ocean, one without edges or emptiness, a sea of invisible waves, where everything that exists is only a ripple on its surface. When you imagine an atom, you might picture a small solar system, a bright centre surrounded by tiny planets in orbit. It's a simple and almost comforting image, but the truth is far stranger and far more beautiful. The atom is not a miniature version of the solar system. It's more like a tiny cathedral built of vibration, light, and probability. A space where existence itself hums quietly between being and not being. If you could somehow shrink yourself down until you were smaller than dust, smaller even than the particles of air that drift through the room, and you floated into the heart of a single atom, what you'd find would surprise you. Most of it would be empty. You'd drift through vast distances of nothingness before you came to the nucleus, that tiny centre where nearly all the atom's weight hides. The distance between the nucleus and the cloud of electrons is so enormous, relative to their size, that the atom is almost entirely space. In fact, if the nucleus were the size of a small marble, the nearest electron would be orbiting several kilometers away. Everything around you, your hands, your pillow, the bed beneath you, is built from emptiness, stitched together by invisible forces that never touch, yet never let go. At the centre, protons and neutrons cluster together, held tight by the strongest force known to science, the strong nuclear force, It's an invisible glue so powerful that if it were even slightly weaker, atoms wouldn't hold, stars wouldn't shine, and no molecule would ever form. You wouldn't be here to wonder about it. It's one of those quiet cosmic coincidences that make existence seem both fragile and deliberate. Each proton carries a positive charge, and each electron carries a matching negative one. They balance each other perfectly, a dance of attraction that defines chemistry itself. Every chemical reaction, from the flicker of a candle to the beating of your heart, is simply electrons rearranging themselves, finding new partners to balance their charge. And here's something even more mysterious. The very shape of the atom, the way its electrons sit in layered shells around the nucleus, follows a kind of cosmic choreography that arises from quantum rules. Those rules say that each electron can occupy only certain energy levels, not anywhere in between. It's as if a staircase connects the nucleus to the edge of the atom, but there are no ramps or landings. The electrons can only rest on the steps themselves. When one jumps from a higher step to a lower one, it releases a small pulse of light, a photon. That light, the simplest whisper of energy, is how atoms talk to the universe. These steps aren't physical rungs you could touch. They're patterns in the mathematics of nature, showing how energy behaves when confined to tiny spaces. If you could listen to them instead of seeing them, you might imagine each electron's movement as a note in an endless melody, sometimes deep and slow, sometimes bright and high. Together they play the harmony of matter, and from those invisible harmonies come everything we can touch. The hardness of metal, the scent of a rose, the colours that bloom when sunlight hits glass. All are born from these tiny leaps of energy inside atoms. Every shade of colour is simply a difference in how much light energy an electron gives off when it moves between steps. When you see blue, you're witnessing a slightly larger leap than when you see red. In a way, colour itself is a translation of quantum music into light. The patterns of atoms also decide how the world feels. The way water flows, how ice freezes, why salt sparkles. All come from the way atoms join hands through shared electrons. These bonds create the vast architecture of matter, from the soft warmth of skin to the cold shimmer of distant planets. And every bond, every molecule, begins in that cathedral of probability, where electrons hum in their chosen orbits, each one following the rules of a quiet universe that seems almost aware of its own balance. Inside the nucleus, the story grows even deeper. The protons and neutrons themselves aren't simple beads of matter. They are made of smaller entities called quarks, which come in flavours with names that sound almost playful. Up, down, strange, charm, top and bottom. Each proton is made of 2 up quarks and 1 down quark. Each neutron holds 2 downs and 1 up. They are held together by particles known as gluons, tiny messengers that carry the strong force, darting endlessly between quarks like threads of light in a tapestry too fast to see. If you could slow down that dance, you'd see quarks and gluons exchanging energy, creating and annihilating tiny bursts of matter and antimatter every moment. They are never still. Even the calmest, coldest atom in the darkest corner of the universe is alive with motion. A restless hum that never stops. This is the quantum heartbeat of reality, a rhythm that underlies everything, and yet, for all this complexity, the atom is remarkably consistent. The same rules that shape the atoms in your body also govern those in distant stars. The carbon that builds your bones was forged inside long-dead suns, squeezed from lighter elements by nuclear fire. When those stars exploded, they scattered their atoms across space, seeding the clouds that would one day form new worlds. Every breath you take carries atoms billions of years old. Every heartbeat stirs elements that once drifted among the stars. You are quite literally made of stardust. The universe condensed into living form. It's a humbling thought, but also a comforting one. Beneath all the complexity, the universe reuses the same simple patterns again and again, across unimaginable scales. Atoms in your body and atoms in a galaxy obey the same quiet laws. When you touch your hand to your chest and feel the warmth there, that warmth is energy flowing through the same invisible fields that power the stars. So the next time you look at something familiar, the soft glow of a lamp, a drop of water catching light, remember that beneath it lies this tiny cathedral, humming in the dark, built from emptiness and yet filled with music. The closer we look, the less we see of matter, and the more we find of motion, of rhythm, of connection. From here, the story opens into something even subtler. Beneath the atoms themselves lies the fabric that makes them possible, a seamless ocean of invisible fields stretching through all of space. Every particle, every flash of light, every touch of warmth is just a ripple in that ocean, a passing note in the universe's quiet symphony. And that is where our gentle exploration will drift next, into the ocean of fields that underlies everything we are. If we drift gently beneath the surface of what we call matter, past the clusters of atoms and the spinning of electrons, we reach a strange kind of calm. It isn't empty, and yet it looks like nothing at all. No particles, no dust, no sound, only potential, a quiet readiness to become. Physicists call this the quantum field, but you can imagine it more simply as an infinite ocean that underlies everything. It stretches through all of space, filling even the darkness between galaxies, and every particle we know is just a small ripple across its surface. The air you breathe, the light in your room, the thought you're having right now, all of it emerges from the same invisible sea. When a wave rises in this ocean, we call it an electron. When another kind of wave trembles, we call it a photon, a particle of light. Each type of particle has its own field, its own way of rippling. You might picture the universe as a vast lake under moonlight, covered with overlapping circles spreading from unseen drops. Where the ripples cross, patterns form, bright, dark, fleeting. That is reality. The name quantum field sounds technical, but its essence is simple. There are no truly empty spaces. Even when we remove every atom, every molecule, every measurable particle, the field remains. It shivers with tiny fluctuations, brief, spontaneous twitches of energy that appear and vanish. They're called virtual particles, though that word virtual can be misleading. They're not imaginary. They're more like whispers of possibility, temporary ripples that the universe keeps breathing in and out. If you could see them, the vacuum itself would sparkle like faint static on an old television screen. Endless points of appearing and disappearing light. We think of space as empty, but the quantum field tells us that nothingness is one of the most energetic states of all. It's never truly still. The energy of these flickering waves is sometimes called zero-point energy, not because it's zero, but because it's the lowest possible level of motion the universe allows. Even at absolute zero, when everything else freezes, the fields still hum quietly in the dark. The strangeness doesn't end there. Each particle you've ever heard of, electrons, protons, photons, neutrinos, is not an isolated object flying through space. It's a local excitement of its field, a pulse that travels like a note through air. A light particle isn't a bead moving from a lamp to your eye. It's a ripple in the electromagnetic field flowing toward you. When that ripple reaches your retina, it doesn't crash. It merges gently into the patterns of your own body's fields. Every interaction is just one wave touching another. When we think of it this way, the borders between things begin to dissolve. Matter and light are no longer separate actors, but movements of one medium. There are no true edges, only shifts in pattern and rhythm. The wall behind you and the air around you are both built from the same sea. Vibrating at different frequencies, their waves arranged in different patterns. It helps to picture this field as woven fabric. Imagine an endless cloth stretched across the cosmos. When it's calm, you see nothing. But when something disturbs it, a passing particle, a beam of light, a breath, ripples spread, fold, and sometimes knot. Those knots become the particles of matter. Those waves are the forces that bind them. Even gravity, the soft curvature that holds galaxies together, may be a kind of trembling in a deeper layer of this cosmic fabric. Sometimes, this sea of fields reveals its presence in subtle ways. The phenomenon known as the Casimir effect, though we won't use the formula here, happens when two metal plates are placed very close together in a vacuum. The plates slightly change the pattern of quantum ripples between them, creating a delicate pressure that pushes them together. It's a quiet reminder that even empty space is full of invisible hands at work. We might ask, if everything is made of fields, why do we see separate objects? Why can you hold a stone, or drink water, or feel the softness of a blanket? It's because the patterns of these fields have become stable, repeating rhythms that persist. Think of a wave caught in a standing pattern, frozen mid-motion. That's what an atom is. A tiny, standing vibration that has found balance. Even you are made of these patterns. The warmth of your skin is the vibration of particles in motion. The light that lets you see is another kind of ripple, touching your eyes and turning into electric whispers inside your brain. The quantum field doesn't end at your body. It flows through you, through your breath, through the space between each heartbeat. You are a wave within waves, part of a rhythm that began long before you were born and will continue long after you sleep. This picture of reality can feel disorienting, even unsettling. It blurs the line between something and nothing, between self and surroundings. But there's a quiet beauty in that blur. It tells us that existence isn't about separateness, it's about resonance. The universe doesn't build itself from pieces the way a child stacks blocks. It builds itself the way music builds harmony, through relationships, through the meeting of waves. When you look up at the night sky, the darkness between the stars is not absence. It's the stage upon which everything plays. The light from those stars is only the visible part of a far larger performance, a song that never ends, a fabric that never rests. Some physicists believe that this underlying field might connect all forces into one unified framework, though that grand theory remains unfinished. Others simply accept the mystery, that the more we learn about the universe, the more it resembles a single, seamless whole. In the end, every experiment, every equation, every observation leads back to the same revelation. There are no true voids, only quieter moments in the same eternal sea. And so, as you breathe and feel the air settle around you, remember that the space between you and everything else is alive with silent motion. The emptiness that seems to separate us is actually what binds us together. From this ocean of fields, everything arises: light, matter, life, thought. If we follow the thread a little further, we'll begin to see how this ceaseless ocean doesn't stay perfectly balanced. Somewhere, in the beginning, a small preference emerged, a lean toward matter instead of antimatter, toward creation instead of erasure. The universe tilted ever so slightly, and from that tiny imbalance came everything we now know. Let's drift toward that story next, the tale of the uneven mirror and how the cosmos chose to exist at all. If we could rewind the story of the universe to its very first seconds, we would find a strange kind of symmetry. For every particle that appeared, there was another, its twin, its opposite, born alongside it. One carried a positive electric charge, the other an equal negative one. They were like perfect reflections facing each other, identical in every detail except the direction of their electric heartbeat. Scientists call this pair matter and antimatter, and together they should have cancelled out completely, leaving behind nothing but light. Yet somehow they didn't. Something in the earliest moments of existence chose to favour one side of the mirror just a little more than the other. That tiny preference, one extra particle for every billion pairs, became everything we see around us now. Stars, planets, oceans, and you. Imagine a dance floor filled with couples moving in perfect rhythm. Every particle spins in step with its partner. When the music ends, they bow and vanish together, leaving the stage empty. But then, in one quiet corner, a single dancer remains, a survivor of the symmetry. That lone dancer is matter itself. It's a poetic way of saying that the entire visible universe is built from leftovers, the tiniest imbalance in a cosmic equation. To understand why that imbalance exists, we need to look closely at what antimatter really is. It isn't dark or evil despite its name, it's just the same kind of stuff, seen through a flipped lens. The particle we call an electron, for instance, has an opposite twin known as a positron. The positron is identical in every way except its charge. When a positron meets an electron, they embrace and vanish in a flash of light. The energy released is the same energy that lights stars and drives every reaction in the cosmos. It's one of nature's simplest and most elegant exchanges. Two become one, and one becomes pure energy. This process happens all the time. High above the atmosphere, when cosmic rays collide with air molecules, small bursts of antimatter appear and disappear. In hospitals, machines called PET scanners use positrons to create detailed images of the body. Even the banana on your kitchen counter releases trace amounts of antimatter as its atoms decay. You're surrounded by this delicate balance between existence and its reflection. The reason we don't notice it is that, in our part of the universe, matter far outweighs antimatter. The mirror broke long ago. What could have caused that break? Physicists have spent decades searching for the reason. Some experiments hint that certain particles, such as neutrinos, might behave slightly differently from their opposites, a subtle asymmetry in how they spin, decay, or interact. These small imperfections could have tilted the balance in favour of matter when the universe was young. It's a reminder that even the grandest of cosmic stories can hinge on the tiniest of details. It's tempting to imagine that somewhere out there, in a distant region of the universe, the opposite occurred, a place made entirely of antimatter, where the laws are the same but the charges are reversed. If such a mirror realm exists, it would look indistinguishable from ours. An antimatter star would shine with the same light. An antimatter person would think, breathe, and dream just as we do. Yet if our two worlds ever touched, even slightly, they would annihilate each other in a brilliant flash of gamma rays. Matter and antimatter are perfect complements, but they cannot coexist in the same space for long. Still, the idea that the universe once balanced so delicately between creation and destruction carries a kind of quiet poetry. The fabric of reality seems to prefer imperfection. Out of perfect symmetry came difference, and out of difference came structure. Without that slight bias toward matter, there would be no galaxies, no warmth, no questions to ask. The universe itself is a celebration of unevenness, a small tilt that allowed time and memory to exist. You can see traces of this asymmetry everywhere. When sunlight touches your skin, it's energy released from the fusion of hydrogen atoms inside the sun, a process that depends entirely on matter's dominance over antimatter. If that balance had been perfect, the sun would have burned away in an instant, leaving only light with no stars to shine. The warmth you feel is the echo of that ancient, imperfect decision. At its heart, this imbalance hints at something profound. The universe seems to have a direction, not in the sense of a destination, but in its flow from simplicity to complexity, from symmetry to variety. It's as though creation needed a small imperfection to begin, a first crack through which everything could unfold. You might even say the cosmos learned to write music by starting slightly off-key. This tilt toward matter also connects us back to the ocean of fields we explored before. Every particle and antiparticle pair is a temporary ripple, born from those fields when energy condenses. For the briefest instant, they rise together like twin waves, one crest, one trough, before merging again. But for reasons we don't yet understand, some waves failed to meet their opposites. They drifted on, carrying the seeds of galaxies within them. In this way, the universe behaves a bit like a painter who accidentally spills colour across a blank canvas. What could have been a perfect void becomes a landscape full of motion and light. Perfection, it seems, is sterile. The universe chose to be interesting instead, and perhaps that's what makes our existence feel so improbable. Because it is. You, me, and everything we know are the children of imbalance. The atoms in your body once fought through annihilation to survive. The carbon that shapes your form was born in a star, which itself was born from that first slight favouring of matter. Every breath you take is a celebration of that cosmic imperfection. When you think of it this way, the universe doesn't feel like a cold machine at all. It feels almost tender, capable of error, capable of asymmetry, and through that, capable of beauty. Perfection was never the goal. Survival was, complexity was, life was. As we drift further into the story, this idea of imbalance will guide us deeper into the quantum world, where certainty itself begins to blur. Just as the universe favoured one side of its reflection, it also seems to favour uncertainty over precision, potential over permanence. The next part of our quiet journey will explore that uncertainty, not as confusion, but as one of the most elegant forms of order nature has ever known. Imagine standing by a quiet lake at dawn. The surface is so still that the first pebble you drop sends rings of ripples all the way to the far shore. You can follow them, one after another, watching how each circle spreads wider and softer until it vanishes into calm again. In a way, this image carries the essence of one of the most delicate truths in all of physics, that everything we look at, everything we measure, sends its own ripple back. The act of seeing changes what is seen. In the early 1900s, a young physicist named Werner Heisenberg realized that this was not simply a matter of clumsy instruments or imperfect measurements. It was something far deeper, woven into the fabric of reality itself. He found that there are pairs of qualities, like where something is and how fast it's moving, that cannot both be known exactly at the same time. The more clearly you see one, the blurrier the other becomes. It wasn't a failure of science. It was a law of nature. But instead of writing it as a hard formula, let's imagine it gently. Picture a small bird in flight. If you focus on the bird's position, catching the exact moment its wings cut through the air, you lose the sense of its motion. You've frozen it. You can't tell how fast or in what direction it's going. But if you follow its movement through the sky, your eyes tracing the pattern of its flight, you lose track of its precise location at any instant. You know its rhythm, but not its coordinates. That's what Heisenberg found in the world of the very small, a dance between knowing and letting go. At that scale, nature doesn't allow stillness. Every electron, every speck of light carries within it a soft vibration that refuses to stop. The universe is never completely still, even when it pretends to be. Trying to measure a particle's place too precisely would mean giving it infinite energy, something the universe doesn't allow, so nature finds balance in blur. You might say the universe protects its secrets by spreading them out, and instead of being frustrating, that uncertainty is what allows motion, change, and life itself. If everything could be pinned down perfectly, nothing would ever move. The future would be locked in, the past unchangeable, and time itself would be a silent, frozen sculpture. Uncertainty instead is like the small gaps between musical notes, the spaces that let the melody breathe. For scientists, this rule became known as the uncertainty principle, but that name hides its softness. It isn't about confusion, it's about coexistence. It tells us that knowledge and freedom are linked. The more tightly you hold one, the more gently you must release the other. The atom survives because its electrons cannot fall neatly onto the nucleus. They hover instead, suspended by this gentle rule of unknowing. Without it, atoms would collapse, matter would vanish, and the world would dissolve back into light. So uncertainty is not a flaw. It is the breath of stability. It's the quiet agreement between the measurable and the mysterious that keeps the universe alive. Think of a foggy morning. You can see the outlines of trees, the shimmer of dew but not their edges. The fog doesn't hide the world, it softens it. That's how the quantum realm appears, not lost to us, just gently veiled, as if the universe prefers suggestion to certainty. And maybe that's why it feels so eerily familiar. We live our lives through a similar veil. You never know exactly what will happen in the next moment, but that doesn't make life meaningless. It makes it open. There's a quiet philosophy hidden inside this science. To measure something is to disturb it. To know it fully is to change it. Every experiment is also a conversation, a two-way exchange between the observer and the observed. In the tinier scales, the world stops being a passive backdrop and becomes a participant. The universe doesn't sit still to be studied, it answers back. And yet, this isn't some mystical idea about consciousness shaping reality. It's simpler and more elegant than that. A measuring device, even without a human behind it, changes the system just by touching it. When you catch a snowflake on your glove, it melts from the warmth of your hand. When you look too closely at the stars, you change the faint light you're trying to capture. Every act of observation carries with it a whisper of interference. At the quantum level, these whispers define what's possible. They set the boundaries of precision and make reality shimmer. When we say that a particle's position and motion can't both be known perfectly, what we mean is that the act of defining one changes the other. The universe is a conversation, not a lecture. And it's in that conversation that the beauty lies. Without uncertainty, there would be no patterns, no emergence, no reason for atoms to spread into complexity. The gentle trembling of unknowing allows the world to unfold, moment by moment, instead of being already written. The future exists not as a fact, but as a cloud of possibilities, waiting for something to nudge it into form. Maybe that's why the universe feels alive, even in its emptiest corners. It is not a machine ticking toward an inevitable outcome. It is a story that retells itself with every interaction. Uncertainty keeps it curious. So the next time you feel unsure about something, remember that even the fabric of the cosmos thrives on uncertainty. It's what gives rise to choice, to freedom, to the warmth of time flowing forward. You're made of that same principle, of things that can never be completely known but are always real enough to touch, to love, to wonder about. In the quiet of night, when your mind wanders between thought and dream, that in-between space is a reflection of the universe itself. Neither here nor there, neither fixed nor lost, just alive, existing in a beautiful maybe. And as we follow the thread a little further, we'll return to the heart of that mystery, to the moment when all those possibilities, all those shimmering maybes suddenly seem to choose. The universe takes a breath, makes a decision, and a single outcome steps forward. That's where we'll go next, to the gentle secret behind how possibility becomes reality. Imagine standing in a quiet concert hall just before the music begins. The air feels charged, as if it's full of unplayed notes waiting to be chosen. Every instrument is ready, every musician holding their breath. For a long moment, the silence isn't empty, it's filled with potential, and then a single gesture brings it all into being. The baton rises and sound fills the space. The universe, at its smallest scale, behaves much the same way. Before something is observed, it exists like that waiting orchestra, a mixture of all possible songs, all possible outcomes, each real but unreal until the moment of contact. This is what physicists call the collapse of the wave function, though it's easier to think of it as the instant when reality chooses a path. Before that choice, the universe is pure possibility, a shimmering fog of maybes. An electron might be here or there, a photon might go left or right, a particle might spin up or down. Every version exists together, layered in the same space, the way several melodies can blend into one soft chord. When something interacts with it, a photon, a detector, even another particle, the chord resolves into a single note. The universe decides, quietly, which version of itself to become. But what does that really mean? It helps to return to our magic box, the one we opened in the very first part of our journey. Remember how the box could contain anything. An apple, a feather, a star, until you lifted the lid. The quantum world is like that box. Before we open it, before any observation takes place, it doesn't hold one definite thing. It holds all of them at once. When we look inside, the world stops being a mixture and becomes a single story. You could picture it as rain forming from a cloud. High above, water exists as vapour, a diffuse, invisible possibility. But as the air cools, the vapour condenses into droplets, each one choosing a path downward. The wave of potential becomes a fall of rain. That transformation from vapour to drop, from superposition to certainty, is what happens every time nature makes a measurement. Some scientists describe this as the moment the wave of probability collapses, not in a violent sense, but like a breath releasing. It's a graceful contraction from possibility into presence. One of the most famous interpretations of this idea came from the Copenhagen school, where Niels Bohr and Werner Heisenberg suggested that physical reality doesn't exist in a definite form until it interacts with something else. In their view, the universe doesn't sit waiting, fully formed and independent. It unfolds through relationships, through observation, measurement, and exchange. That doesn't mean we create reality simply by looking. It means that observation is participation. To measure something is to join its story. Whether it's a particle meeting a detector or light bouncing off a leaf into your eyes, each act of contact turns a blur of probabilities into one visible world. If this seems unsettling, it's worth pausing to notice how natural it really is. You experience something like this every day. Think of a dream just before waking. When you're asleep, the dream is fluid. People change faces, places blur, time bends. But the moment you open your eyes, the dream collapses into memory. The fog solidifies into one version of events, leaving all the others behind. That's the feeling of wave function collapse, the gentle narrowing of possibility into the comfort of now. And yet, what exactly counts as observation remains one of the great mysteries. Does it require consciousness, a mind aware of the outcome? Or is the simple act of interaction enough? Imagine a tiny particle detector clicking in a lab, registering an event and no human will ever see. Did reality still choose in that moment? Most physicists say yes. The act of interaction alone is enough. Consciousness may notice, but it doesn't have to command. There's a quiet beauty in that idea. It means that the universe is constantly making choices, moment by moment, everywhere, even when no one is watching. Stars shine because waves of a light collapse into certainty when they strike matter. Plants grow because photons choose their paths into leaves. Even the warmth on your skin right now is the outcome of countless tiny decisions. Energy resolving itself from potential into presence. If you could slow time down and watch this happen, you'd see a dance more intricate than any orchestra's performance. Waves of probability spread outward from every event, overlapping and merging. Then, each time two waves meet, when one particle touches another, the universe pauses, chooses, and continues on. It's as if reality itself plays an endless improvisation, where each note changes the next. What collapses in these moments isn't the world itself, but our uncertainty about it. The equations of quantum physics, when translated softly into words, describe this process as a balance between what can happen and what does happen. Every interaction narrows the possibilities, but it never eliminates wonder. Even after collapse, the next moment begins with new uncertainty, new potential. Reality breathes in and out, expanding into possibility, contracting into decision. There's a quiet poetry in how this mirrors our own lives. Every day we live in superposition, a dozen paths branching ahead, choices still unmade. Each decision, to speak, to stay silent, to turn left or right, collapses those paths into a single thread we call experience. But the potential for change never ends. The next moment always opens again to possibility. In that way, our lives follow the same rhythm as the universe. A steady pulse of perhaps, followed by a soft yes. Scientists still debate what truly happens when a wave function collapses. Some say the collapse is only apparent, a kind of illusion born from the limits of our perspective. Others insist it's a real physical process, like a coin flipping and landing on one side. But perhaps it's both, a truth that's more about harmony than argument. In the end, quantum physics doesn't ask us to choose between mystery and meaning. It simply invites us to listen to both at once. So the next time you find yourself caught between options, uncertain, undecided, you might remember that even the smallest pieces of the universe are comfortable with ambiguity. Possibility isn't a flaw, it's the natural state of things. Reality, it seems, is less like a finished picture and more like a melody still being written. And as we drift further into this story, that melody will take on a stranger tone, one that hums softly between worlds. It's a story of a cat, a box, and the peculiar space between life and death. A story that began as a thought experiment and became a symbol of everything both terrifying and tender about uncertainty itself. Imagine, for a moment, a quiet room. The curtains are drawn. A single box sits on a table, its lid closed, perfectly still. Inside the box, there's a cat, or so we're told, but we don't know whether the cat is awake or asleep, purring or silent. The box doesn't say, it just sits there, patient, unbothered by our curiosity. You might be tempted to lift the lid and find out, but in this story, the act of looking isn't just discovery, it's transformation. This is the famous thought experiment proposed by the Austrian physicist Erwin Schrödinger in 1935, created not as a literal tale, but as a question, maybe even a protest, against the way quantum mechanics describes the world. According to the theory, a particle can exist in many possible states at once. An electron can be here and there, spinning this way and that, until it is observed. Then, with a kind of quiet finality, it chooses a single version of itself. Schrödinger wondered, if this is really true, what would happen if the rule were scaled up to something we could see, like a cat? He imagined a simple but haunting setup. Inside the box sits a small container of poison gas, sealed and harmless. Next to it, a device that can break the container if triggered by the decay of a single radioactive atom. The chance of that decay happening within an hour is 50%, a coin toss of nature. If the atom decays, the gas is released and the cat dies. If it doesn't, the cat lives. From our point of view, with the box still closed, both possibilities are true. The cat is alive and dead at the same time. Not in a metaphorical sense, but literally, until the box is opened and the story resolves into one outcome. Of course, Schrödinger didn't actually plan to harm any cats. His experiment was a kind of thought mirror, designed to show how strange the quantum world seems when applied to everyday life. It was his way of saying, surely this can't be the full story. But nature, in its gentle stubbornness, has kept us guessing ever since. The cat in the box became more than a paradox. It became a symbol of the boundary between the quantum and the classical, between the realm of maybe and the realm of must. In the world of atoms, superposition is normal. In our world of apples and chairs and sleeping cats, it feels impossible. So what happens in between? Where does the fog of uncertainty fade into the solidity of the familiar? In recent decades, scientists have begun to create their own cat states, though without any living animals involved. They trap atoms, photons, or even small groups of molecules and coax them into being in two or more states at once, spinning clockwise and counterclockwise, moving left and right, existing in overlapping places. Then, by carefully measuring them, they watch how the superposition collapses into a single state. The more complex the system, the faster that collapse seems to happen. It's as if the world itself doesn't like ambiguity when too many players join the game. The process behind that fading of possibilities is called decoherence, but we don't need the word to feel its meaning. It's what happens when delicate patterns lose their isolation, when the quiet of the quantum is disturbed by the noise of the environment. You could picture it as ripples on a pond. If you drop one pebble, you see clear circles spreading out. Drop a handful, and the ripples interfere until the surface becomes chaos. Superpositions are like those perfect circles, fragile and fleeting. The moment they touch the wider world, they blur into the ordinary. There's something oddly comforting about this. It tells us that the universe protects its mysteries, but only for a time. When conditions are calm enough, when things are cold, small and quiet, the quantum dream shines through. When they grow larger, warmer and noisier, the dream fades into the steady hum of everyday physics. It's not that the rules change, but that they blend. The quantum and the classical aren't enemies. They're chapters of the same story told at different scales. Still, the cat remains in our imagination, waiting between states. Some physicists say that superposition never truly ends, that both outcomes continue to exist in parallel branches of reality, each as real as the other. In one branch, the cat stretches and yawns. In another, it lies still. The only thing that changes is which branch we find ourselves in. It's a comforting idea for some, a dizzying one for others. But perhaps the point of the cat is not to demand an answer, but to invite humility. The thought experiment reminds us how small our intuitions are compared to nature's complexity. Our minds crave certainty. Is the cat alive or not? Nature, with a quiet smile, replies, yes. If we look at the story another way, it's also about participation. Before you open the box, the cat's fate is suspended in possibility, not yet decided, but also not meaningless. Your choice to look, to ask, becomes part of the outcome. The world is always in conversation with us, not a stage frozen in advance, but a dialogue in progress. Every act of attention shapes what follows, even in small, imperceptible ways. And maybe that's what makes this idea linger in so many hearts. It isn't just about physics, it's about being alive. We too live in a kind of superposition. Each morning holds countless possibilities. What we might say, who we might meet, what we might become. Every decision we make collapses those maybes into one lived reality. Like Schrödinger's cat, we exist in the tension between the infinite and the specific, between potential and the moment we choose to look. You could even think of life itself as a series of gentle collapses, a chain of wave functions resolving into experience. Each choice we make doesn't destroy the other possibilities, it simply lets one of them take form. The rest linger softly in the background of what might have been. As we sit with this image, the cat breathing in both worlds, the edges of science and philosophy blur once again. The universe, it seems, is both playful and profound. It allows contradiction yet never chaos. It whispers that uncertainty isn't an error but an art form, and whether the cat is truly alive or dead is less important than the realization that both possibilities coexist in the same patient box, until the world decides to open the lid. From here, our quiet exploration turns toward what those choices mean. Scientists have proposed many interpretations of these mysteries, different stories told about the same equations. Some say the world collapses, others say it branches infinitely, A few imagine hidden tides guiding every motion behind the scenes. Each explanation paints a different portrait of the same elusive truth. And so, as we leave the cat resting in its paradox, we'll step softly into the minds of those who tried to make sense of it, the philosophers of physics who turned uncertainty into wisdom. The trail of clues leads us gently into the question, if reality can tell so many stories, which one, if any, is true? If we pause here and listen closely, we might hear the quiet voice that guided much of early quantum theory, the calm, steady voice of Niels Bohr. His students once said that speaking with him felt like walking through mist. You didn't always know where you were headed, but the air itself felt full of meaning. Bohr belonged to that rare kind of thinker who could look directly at paradox and simply smile. Where others saw contradiction, he saw balance. Where others demanded certainty, he whispered patience. He called his way of seeing the world complementarity, a word that sounds abstract but feels almost musical. It means that two seemingly opposite descriptions can both be true, depending on how you look. Light, for instance, behaves like a wave in some experiments and like a particle in others. But for Bohr, this wasn't a failure of understanding. It was a sign of the universe's generosity. Nature was offering us two languages, not one, and both were needed to tell the story. The Copenhagen interpretation, named after Bohr's home city, took shape around this philosophy. It suggested that the mathematics of quantum theory does not describe what is out there before we look, but what we can say about what we observe. In this picture, the act of measurement isn't an intrusion on reality. It's the bridge between possibility and experience. The world doesn't reveal itself fully formed, waiting to be discovered. It reveals itself through our questions, one gentle answer at a time. To some, this idea felt like surrender, as if physics had stopped seeking truth and settled for probabilities. But Bohr didn't see it that way. He once said, "Physics is not about how nature is, but about what we can say about nature." He meant that humility is not weakness. It is alignment. By accepting that our language, our tools, and even our senses are part of the experiment, we allow reality to speak in its own quiet voice. You can imagine Bohr's approach as a kind of musical discipline. A musician doesn't need to know how every atom in a violin moves to play a beautiful note. It's enough to know how the instrument responds to touch, to pressure, to timing. In the same way, quantum physics doesn't need to map the entire hidden interior of reality. It only needs to understand how the universe responds when we reach out. The melody is real, even if the sheet music is invisible. When we say the wave function collapses, the Copenhagen view doesn't treat this as a physical explosion or a literal snapping of possibilities. It's simply the moment when the story becomes specific, when the symphony chooses a single chord. Before that, the universe hums with overlapping tones. Afterward, one clear note lingers in the air. It's tempting to ask, but what's really happening underneath? Where do those possibilities go? Bohr would likely smile again and say, perhaps the question itself doesn't belong to the world we can measure. It isn't that there's no deeper layer, but that the tools we have, rulers, detectors, equations, cannot cross that threshold. They are built for relationships, not absolutes. They measure the song, not the silence between the notes. For Bohr, this wasn't a flaw to fix. It was the natural shape of human understanding. The observer and the observed are two sides of the same mirror. You can't see your own reflection without standing in front of it, and you can't separate your gaze from what it illuminates. Physics, then, becomes a shared act of creation, a dialogue between curiosity and the cosmos. In this interpretation, the universe feels less like a machine and more like a poem. It doesn't hand over its secrets on demand. It speaks in hints, in starlight and patterns, in the hum of atoms and the rhythm of orbits. Each observation is like turning a page in that poem. The words rearrange themselves as you read. The meaning changes depending on how softly you look. This way of thinking might sound frustrating to those who seek absolute truth, but for Bohr, it brought peace. He believed that knowing the limits of our knowledge was the highest form of wisdom. Every valuable human being, he once said, must learn to live in a state of balance between courage and humility. Quantum mechanics was, to him, an invitation to practice that balance, to hold the known and the unknown together without forcing them to collide. The Copenhagen interpretation does not demand that you imagine parallel universes or hidden mechanisms beneath the surface. It simply asks you to accept that reality and knowledge are intertwined. The world becomes definite only through interaction. Beyond that, asking for certainty is like asking music to freeze mid-note. You might feel that this view turns the universe into a dream, but maybe that isn't such a bad thing. Dreams are coherent within their own rules, consistent in their own language. They don't need to explain themselves. Perhaps the quantum world is the universe dreaming in equations, and what we call measurement is the moment we briefly share that dream. If this still feels abstract, think of how you experience light. When you turn on a lamp, you don't see a stream of particles hitting your eyes. You see a room filled with warmth. That glow is the result of countless quantum interactions, photons collapsing into your perception of colour. The physics beneath it is uncertain, but the experience is real, tangible, comforting. That is the Copenhagen calm. The acceptance that reality doesn't need to be perfectly understood to be beautifully consistent. When you take a slow breath and look around, everything you see is the sum of millions of such collapses, each one an agreement between matter and awareness, energy and form. The world feels solid because it's been observed, shaped gently by endless interactions that brought it into focus. Bohr's approach reminds us that curiosity and humility are not opposites. They're partners in the same dance. We measure because we want to know, but we listen because we understand that knowing is always partial, and that partial knowing is enough to fill the world with wonder. As we drift further into the story, we'll step from Bohr's calm pragmatism into a stranger landscape, one where the universe may never collapse at all, but instead keeps every possibility alive. Some physicists began to imagine reality as a vast branching forest of worlds, each growing from every quantum choice. In this view, nothing is lost. Every version of the cat, every path of the photon, every whisper of uncertainty, all continue side by side. And so, the next part of our journey carries us softly into that forest, where all possibilities live together beneath an infinite sky. Imagine standing in a forest at night. The moonlight filters through the trees, painting silver paths in every direction. You take one step forward, and for a moment you hesitate, wondering what would happen if you turned left instead of right, if you paused instead of moving. The forest doesn't answer, but somewhere, in a version of the story you'll never see, another you takes that other path, and both steps are real, echoing softly through different clearings of the same endless woods. This is the picture that grew from Hugh Everett's mind in the 1950s, the many worlds interpretation of quantum mechanics. It begins with the same mystery that haunted Bohr and his colleagues. What happens when a wave of possibilities collapses into one result? Everett's answer was bold and beautifully unsettling. He suggested that nothing collapses at all. The universe doesn't destroy possibilities, it simply unfolds into all of them at once. Every outcome of every event exists, just not all in the same branch of reality. In Everett's view, the act of measurement doesn't narrow the world to a single truth, it multiplies it. When a particle can go left or right, the universe doesn't choose, it splits. In one branch it goes left, in another, right. When you flip a coin, both results happen, one world for heads, one for tails. When Schrödinger's cat faces its paradox, both versions of the story live on, one where it wakes and stretches, one where it falls still. You, the observer, split as well, following each outcome in your own separate thread. To visualize it, think of the universe as a tree. Every quantum event is a branching point, a new twig, a new leaf, each carrying its own continuation of the story. From afar, the tree looks whole and continuous. Up close, it's a labyrinth of forking paths, every choice preserved, every possibility given space to breathe. It's a poetic picture, and also an immense one. The many worlds interpretation implies that there are more versions of the universe than grains of sand, than atoms in all the stars combined. Every decision, every random flicker of energy, every measurement ever made has spun the cosmos into countless parallel melodies. Some might find that overwhelming, even lonely, the idea that every moment of your life splinters into infinite others. But there's a gentler way to hold it. You can think of it as the universe being too generous to waste a single possibility. Instead of asking, which world is real? Everett invites us to consider that all of them are, each equally valid, each telling its own story. We simply experience one thread because our awareness flows through it like a river through a single valley. We can't see the other streams, but we can sense their presence, a faint chorus just beyond hearing. And although this sounds like philosophy, it arises directly from the mathematics of quantum theory. The equations describing the evolution of a wave, when written without the idea of collapse, naturally contain every possible outcome. Everett simply took that literally. To him, it wasn't that the universe chooses one reality. It's that reality is already vast enough to contain them all. It's a radical act of inclusion. Instead of cutting away possibilities, the universe keeps them. It doesn't delete the paths not taken. It weaves them into the background of existence. You might say it's an economy of imagination, where nothing is wasted. For some scientists, this view offered relief. It resolved the strange tension of collapse. No mysterious observer, no sudden choice. The equations simply run forward, smoothly, logically, endlessly. For others, it was too much, too infinite, too indifferent to our need for simplicity. They asked, if these countless universes exist, why can't we reach them? Why can't we test this? The answer, softly, is that every branch is self-contained. The pairs don't cross once they've parted. Like notes in a chord, they resonate together but never overlap. Still, the idea has endured, not just because it's mathematically neat, but because it stirs something in the human spirit. It whispers that all the lost chances, all the choices we never made, might still live somewhere, still unfolding, still real. The life where you said yes instead of no, the conversation you never had, the dream you didn't chase, all of them, perhaps, are being lived by another version of you in another branch of the same cosmic tree. It's a haunting, beautiful thought, that existence is not a single thread but a woven tapestry. And yet, like most of quantum mechanics, this view doesn't claim to comfort. It simply describes. It invites awe, not certainty. The universe, under this interpretation, is endlessly branching, but each branch is complete within itself, requiring nothing more than the quiet awareness of its own unfolding. You might wonder if this makes our choices meaningless. If everything happens somewhere, what does it matter what we do here? But meaning doesn't vanish in infinity, it concentrates. The branch you live is still yours. Your experience, your kindness, your small victories are not diminished by the possibility of others. In fact, they are made more precious by knowing how many other paths exist. Amid infinite possibilities, this one, your one, is unique in its immediacy. Perhaps this is why the many worlds idea continues to resonate beyond physics, because it mirrors the way we already experience life. We live surrounded by unchosen paths, haunted by what if, dreaming of alternate lives that shimmer just out of reach. In that sense, Everett's universe is not an alien idea at all. It's simply a magnified reflection of our own imagination, extended to the stars. As we listen to this branching forest, it's worth noting that the many worlds interpretation doesn't contradict the calm of Copenhagen. They describe the same music from different angles. One focuses on the note we hear, the other on the full harmony of all that could have been. Both are true depending on how softly you listen. Somewhere perhaps another version of you has already drifted to sleep while hearing these words, dreaming of a forest filled with endless paths, each glowing faintly in the moonlight. And maybe that's the point. The multiverse isn't a place to visit. It's a way of understanding the generosity of reality, its refusal to discard any possibility, no matter how small. From here, our quiet exploration turns toward a different kind of comfort, a return to the idea of hidden order beneath all this branching. Some physicists could not accept a world so vast and uncertain. They searched instead for a steady current beneath the waves, an invisible tide that guides every particle and restores a sense of direction. As we drift onward, we'll follow that whisper, toward the hidden waves that might still shape the story behind the scenes. If you stand by the shore on a still evening, you might notice how the sea moves even when there's no wind. The waves roll in gentle rhythm, as though guided by something far away, something deeper than a surface breeze. To some physicists, this image of hidden motion beneath visible calm felt like a truer way to understand the quantum world. They believe that particles do not drift aimlessly through fields of probability, but follow invisible currents, quiet and precise. This was the idea that became known as the pilot wave theory, a name that sounds mechanical, but really it's more like poetry. The idea was first proposed by the French physicist Louis de Broglie in the 1920s. He was one of the first to imagine that every particle, every bit of matter travels not alone, but accompanied by a subtle wave, a kind of invisible companion that tells it where to go. The particle itself is like a small boat, and the wave beneath it is the ocean guiding its path. This was de Broglie's quiet rebellion against the uncertainty that defined quantum mechanics. He didn't want to abandon determinism entirely, the comforting thought that things move for reasons, not just by chance. He wanted to find a middle way, a story that still allowed for predictability, but softened by mystery. Later, the physicist David Bohm took de Broglie's concept and gave it new depth. He saw the universe as a kind of great wholeness, where everything is connected to everything else through a hidden order, what he called the implicate order. In this view, what we see, the moving particles, the flashes of light, the steady patterns of atoms, is only the surface. Beneath it lies a vast ocean of unbroken unity. The world of appearances, the one we can measure, is the explicate order, like the waves on the water's surface. But beneath that surface, invisible and continuous, the deeper current, the implicate, moves through everything, connecting all forms and all events. Bohm believed that what we call randomness might simply be the limits of our perception. Imagine watching a leaf float down a river. From where you stand, its motion seems erratic, twisting, circling, pausing. But if you could see the invisible whirlpools beneath the surface, you'd understand why it moves that way. Every motion has a cause, hidden just below what's visible. In the same way, Bohm suggested that the strange behaviour of particles might not be truly random, but guided by subtle information encoded in those underlying waves. This information isn't written in words or symbols, it's carried in patterns, in rhythm, in phase, in harmony. You might picture it as the way sound travels through air. You don't see the compression of molecules that make a song, but you feel its rhythm in your bones. The universe, in Bohm's view, works like that. A vast resonant medium through which meaning flows silently. It's a comforting thought, especially after wandering through the many worlds of infinite branching. In Bohm's universe, there's still unity. Everything, from the smallest quark to the farthest galaxy, participates in a shared movement. Particles are not lonely wanderers, they're connected by the sea that holds them all. When one moves, it ripples through the rest. When you lift your hand somewhere, in ways we can't measure, the fabric of the cosmos shifts to accommodate the gesture. The mathematics of Bohm's model, though we'll leave the numbers aside, describes how each particle's trajectory depends on the shape of its guiding wave. That wave, in turn, depends on the configuration of all other particles. Nothing is truly separate. It's an elegant loop of influence, each part shaping the whole, and the whole shaping each part. In this sense, the pilot wave theory isn't a denial of quantum mechanics, it's a reinterpretation, one that reintroduces quiet determinism beneath apparent chaos. But Bohm's deeper contribution was not only in physics, it was in philosophy. He believed that our way of thinking, our tendency to cut the world into separate pieces, to divide rather than to see connection, was itself a limitation. The fragmentation of thought, he wrote, is what prevents us from seeing the wholeness that already exists. In other words, the universe doesn't have to be pieced together. It already is one seamless field. It's our perception that creates edges and boundaries. You might compare this to a tapestry viewed too closely. Press your eyes to the threads, and all you see are colours without pattern, fibres without meaning. Step back and the image appears, not separate strands, but a single woven design. In the same way, Bohm's vision invites us to step back from the rush of separate phenomena and see that the world, in its essence, is one vast motion, folded and unfolded in infinite ways. This folding is another way he described reality. He imagined that the implicate order continually unfolds and unfolds into the explicate, that everything visible is like a sheet being folded into itself, carrying within it the memory of all that came before. Just as a hologram contains the image of a whole object in every fragment, the universe, in his model, contains the whole in every part. Every atom, every person, every moment carries traces of the total pattern. There's something quietly spiritual about this, though Bohm never intended it as mysticism. He simply saw physics as another way of asking an ancient question. How does the one become the many? And how do the many remain one? His pilot wave universe might never be provable in a final, absolute sense. No experiment has yet shown the hidden currents he imagined. But even as a metaphor, it offers a gentle wisdom, that what seems random might be woven, that what feels separate might be singing in harmony. It tells us that perhaps beneath every act of chance, there's a hidden rhythm we can almost feel, like the steady pulse beneath a piece of music. When you walk along the shore, the waves you see breaking at your feet are shaped by winds that began thousands of miles away. Their source is invisible, but their effect is undeniable. So it may be with the quantum world, with every particle, every decision, every flicker of light. The surface is chaotic, but the depths are calm. And if that's true, then maybe our lives are like that too. We often see only the turbulence, the chance meetings, the missed opportunities, the coincidences that feel senseless. But perhaps beneath all that, something subtler is guiding us, some deep pattern we haven't yet learned to read. From here, our journey begins to lift from physics into reflection. Whether the universe is ruled by hidden waves, branching worlds, or quiet collapses of probability, one truth seems to echo across them all. Everything is connected through observation, through relationship, through the act of noticing. The story of quantum mechanics, at its heart, is not about isolation, but entanglement, a cosmic intimacy that defies distance. So, as we follow that thread, our next steps will take us into the most delicate of all those connections, the phenomenon that Einstein himself once called spooky action at a distance. We'll drift into the world of entanglement, where two particles can share a single thought across the emptiness of space, and the universe reminds us that separation may only be an illusion. Imagine two tiny sparks born together in the same moment, a pair of particles created from a single flicker of energy. For an instant they exist side by side, perfectly connected. Then, as if the universe breathes, they drift apart. One carried to the left, the other to the right, until miles, or perhaps even light years, stretch between them. You might think their story ends there, each particle wandering alone through space, but somehow they remain connected in a way that no distance can erase. When one turns, the other turns too. When one spins, the other seems to answer, as though they're still whispering to each other across the void. This mysterious relationship is called quantum entanglement. Though the name hardly captures its grace, it doesn't mean that the particles are tied by some invisible string, or that they send secret messages faster than light. Instead, it means that they share something deeper, a pattern, a memory, a kind of shared rhythm. They are not two separate things anymore, but two expressions of a single larger story. To understand this, imagine rolling two dice that were somehow linked together. You toss one in your hand and send the other far away, across a city, perhaps across the planet. When both dice land, they always show matching numbers. Roll again, and the pattern continues, every time, perfectly. You might think there's a trick, a hidden wire, a signal being passed in secret. But in the quantum world, there's no message being sent. The dice were never independent to begin with. Their outcomes were written together from the start, like two lines in a poem that rhyme even when read apart. Albert Einstein didn't like this idea. He called it spooky action at a distance, not because he thought it was magical, but because it defied his sense of how nature should behave. To him, the universe made sense through locality, each thing affecting its neighbours through signals that travel no faster than light. Entanglement seemed to break that rule. How could two particles separated by galaxies know instantly what the other was doing? Einstein believed there must be something hidden, a deeper layer of information we hadn't yet discovered, small gears turning behind the curtain to explain the match. He was sure the world was complete, that the universe wouldn't play dice without reason. And yet, experiment after experiment kept showing that these strange correlations were real. When physicists measured one of the entangled particles, say its spin or orientation, they found that the other always responded in perfect harmony, even when separated by vast distances. The moment one outcome appeared, the other was already written. It wasn't communication, not in any ordinary sense. It was more like two dancers performing the same choreography, perfectly synchronized, even when they can no longer see each other. The secret lies not in what travels between them, but in how they begin. Entangled particles are born together from the same event, the same energy, the same mathematical description. In the soft language of quantum physics, they share a single wave, a single probability cloud that extends across space. When we measure one, we don't cause a message to travel to the other. We simply reveal a truth that already belonged to both. Their connection isn't across space, it is space, woven into its very fabric. It helps to imagine them not as two separate objects, but as two notes in the same chord. You can pluck one string and hear its twin resonate across the room. The air between them carries no visible bridge, yet the harmony exists all the same. That's what entanglement is, harmony written into the architecture of reality. What makes this idea even more remarkable is how delicate it is. Entanglement can be lost, broken by the faintest disturbance, a stray photon, a passing atom, even the warmth of a nearby hand. But while it lasts, it binds particles in perfect unity, no matter how far apart they drift. This quiet loyalty of nature has now been demonstrated countless times in laboratories around the world. Scientists send entangled photons through fiber cables, bounce them off satellites, even use them to create early versions of quantum communication. Each experiment seems to whisper the same thing: connection is more fundamental than separation. And yet, there is a quiet catch. Entanglement doesn't let us send information faster than light. The instant correlations might look like instant communication, but they aren't. You can't control which outcome you get on one side, and without that control, no signal can be sent. It's like two friends agreeing to flip coins. They always get opposite results, but neither can use that to talk to the other. What the phenomenon reveals is not a loophole in the speed limit of the universe, but something deeper, that reality doesn't need to send messages to stay consistent. The pattern is already whole before the measurement begins. When you look at the night sky, you might see stars scattered across the vastness, each shining alone. But beneath that glittering distance, the same cosmic fields hum through all of them. In that sense, entanglement isn't strange at all. It's a reminder that the universe has always been a single fabric, stretching beyond our ability to see the threads. The atoms in your hand and the atoms in the stars are still part of that same pattern. Their separateness is an illusion of perspective. It's easy to think of entanglement as cold or mathematical, but there's an almost tender feeling to it. The idea that two things can remain in perfect agreement, no matter how far apart they travel, carries a quiet comfort. It suggests that distance might not be the opposite of closeness, and that what we call isolation may be only a surface impression. You might even think of memory itself as a kind of entanglement, the mind keeping a connection to what is gone. When you recall someone's voice or a moment of warmth, you reach through time, not by sending a signal, but by feeling the pattern that still lives inside you. Nature, it seems, remembers in its own way too. Entanglement has become one of the most tested and reliable features of the quantum world. It isn't just a curiosity, it's the foundation of the technologies that will soon shape the future. Quantum computers, teleportation of information, unbreakable encryption. But beneath those applications lies something far more profound, a quiet truth about how existence works. Nothing in the universe stands entirely alone. Every particle carries within it the echo of its birth, a memory of connection, a gentle pull toward coherence. So as you lie here listening, imagine the space around you, the air, the walls, the stars, not as emptiness, but as threads of one great tapestry. The particles that make you are still entangled in some distant, fading way with those that once shared their beginnings in ancient stars. You are part of the same quiet pattern that hums through all things. And as we drift a little deeper into that idea, we'll see how scientists try to test this mysterious harmony, to ask whether the universe truly behaves like one grand connected song. The answer, as it turned out, revealed not chaos, but an even more elegant unity, one that would make even Einstein pause in wonder. Imagine two musicians standing on opposite sides of a great valley, their instruments tuned before dawn. They cannot see each other, cannot signal, cannot share a single note through the morning fog, yet when they begin to play, their songs match perfectly. Every pause, every shift in rhythm, every rise and fall of melody synchronized as if by invisible design. You might think they had practiced together in secret. But what if they had never met? What if their harmony was not planned at all, but built into the very strings of their instruments? That is the kind of mystery that John Bell, a quiet, thoughtful physicist from Northern Ireland, set out to explore in the 1960s. He was haunted by the same question that unsettled Einstein. Could the universe really be so connected that one particle instantly knew what another was doing, even across galaxies? Or was there a subtler explanation, something hidden underneath, a local mechanism that made those perfect coincidences seem magical when they were not? Einstein had believed in what he called local realism, the idea that reality exists independently of observation, and that nothing influences anything else faster than light. He imagined that perhaps the entangled particles carried secret instructions from the start, like identical twins given the same script before setting out into the world. When one was measured, it didn't have to communicate with the other, it simply followed the part it had always been given. Bell wanted to test that intuition, to see if hidden instructions could really explain the perfect harmony of entanglement. But how do you test the invisible? Bell realised that the answer lay not in watching single events, but in comparing patterns over many. He designed a thought experiment, later turned into real ones, involving pairs of entangled particles sent to two detectors placed far apart. Each detector could measure the particles in different ways, like asking two musicians to play different notes. If hidden instructions existed, certain combinations of measurements would produce correlations that obeyed a predictable limit. That limit became known, in mathematical form, as Bell's inequality. But in softer words, it meant this: if the world is built only from local causes, there are boundaries to how strongly distant events can mirror one another. When the first experiments were performed in the 1970s and 1980s, they already hinted that nature didn't care much for those boundaries. The correlations between entangled particles were stronger than any local rule could allow. But scientists are careful people. They look for loopholes, tiny cracks in experimental design that might let coincidence sneak in. Over the next few decades, new experiments tightened every seal. Detectors were improved, distances increased, random choices made faster than light could travel between them. Then, in 2015, a team in Delft, the Netherlands, conducted what many called the first truly loophole-free Bell test. They created entangled electrons in tiny diamonds, separated them by over a kilometre, and measured them at nearly the same instant. No signal, no hidden note could have passed between them, and yet, once again, their outcomes matched with perfect precision. Nature, it seemed, refused to obey the limits of local realism. The melody across the valley remained flawless. This didn't mean that particles were sending messages faster than light, or that information was travelling through some hidden tunnel. It meant something subtler, that the universe itself might not be built from separate independent parts. The particles weren't coordinating their answers, they were simply expressing a single, shared state that stretched across space. It wasn't communication, it was coherence. Bell's result, when spoken softly, tells us that the world is not a collection of isolated things bumping into one another, but a network of relationships, a pattern that holds its shape even when stretched across unimaginable distances. Local realism, the comforting idea that everything has its own self-contained reality, independent of everything else, falls away under this light. The universe, it turns out, is a web that cannot be untangled. For some, this realization feels unsettling, as though individuality itself dissolves into cosmic sameness. But perhaps it's the opposite. Maybe this connection is what makes individuality possible, the same way that a note gains meaning only within a chord. The universe doesn't blur things together, it binds them in relationship. You, me, every atom, every photon are woven into that same pattern of correlation. It's important to remember that this deep linkage doesn't let us break any cosmic speed limits. No usable signal passes through the entanglement. It remains silent, private, almost polite. It's as if the universe wants to show us how deeply things are connected without letting us use that connection as a shortcut. The silence itself is part of the design, a gentle reminder that not all communication happens through words or energy. Some messages are written simply in symmetry. Einstein, who passed away a decade before Bell's theorem, never saw these experiments, but if he had, one imagines he might have sighed, half in defeat, half in admiration. For all his resistance to spooky action, he loved elegance, and Bell's work was nothing if not elegant. It didn't destroy Einstein's dream of reason, it expanded it. It showed that the universe's logic is not local, but holistic, a logic of relationships rather than things. You can feel this same principle in your own life if you look closely. Think of the moments when you've reached for the phone just as someone was about to call, or when you've thought of a friend seconds before they wrote to you. These aren't scientific examples, of course, but they remind us how often our minds sense connection long before we can explain it. The cosmos seems to hum with coherence, and sometimes, if you listen carefully, you can hear a faint echo of that song in the spaces between thought. In the end, Bell's theorem doesn't tell us why the universe is connected, it only proves that it is. The mathematics translates, in plain language, to this quiet sentence. The world is stranger and more unified than our intuition allows. When one part moves, the rest adjusts, instantly, seamlessly, without protest. And that truth feels less like a threat and more like a promise. It means that nothing ever truly acts alone. Every star that collapses, every atom that vibrates, every heartbeat that stirs contributes to a shared rhythm that fills the cosmos. Even the space between things, the emptiness we once thought divided them, is now revealed to be part of the connection. As we follow this trail of wonder, our path leads naturally to reflection. If every particle can remain linked to its twin across the universe, perhaps separateness itself is an illusion, a convenient story told at human scale. The next step in our journey will be to explore that story and to see what it means for us, the observers, who also exist inside this seamless web. If you could step back far enough to see the universe as a single picture, you might notice something that no telescope has ever captured: a quiet sense of togetherness. From the smallest spark of energy to the largest cluster of galaxies, everything seems to move as if listening to the same rhythm, bound by an invisible thread of coherence. We usually imagine the universe as a collection of separate things, stars there, people here, empty space in between. But the more deeply we look, the more that separation begins to dissolve. Entanglement showed us that particles can share a kind of hidden companionship that distance cannot weaken. Bell's experiments reveal that this companionship isn't a trick or an illusion. It's the way nature actually behaves. Every piece of reality seems to remember its connection to every other piece. It's as if the universe has always known that it could never be alone. We tend to think of connection as something fragile, like a rope that can be cut or signal that can fade. But the connections that hold the cosmos together are different. They are not transmitted through space. They are space. The fields that make up reality stretch across everything, and entanglement is just a reminder that those fields never truly break. You and I, the air around us, the light that glows between stars, we're all made from the same trembling medium. When one part quivers, all the others feel it, even if only as the faintest whisper. Sometimes this idea can sound mystical, but it isn't magic. It's simply the mathematics of coherence translated into language we can feel. The equations describe relationships, not things, and those relationships form patterns of symmetry, like the resonant lines of a song played on infinite instruments. You don't need to picture the notes as travelling anywhere. They arise together, woven into the same melody. You might wonder, though, what does this mean for us, for the world we experience? Does it matter that distant atoms are somehow still aware of each other? Perhaps it matters more than we realise, because at its core, entanglement reminds us that the boundaries we draw are practical, not ultimate. The edge of your body, the border of a planet, the rim of a galaxy. These are useful for conversation, but not for truth. In the deepest sense, there are no edges, only continuities. Think of the wind. You can feel it brush against your face, yet you can't say where it begins or ends. The air moves as one, guided by unseen pressure and temperature and flow. Our lives are like that too, individual currents in a larger atmosphere of being. We act, we speak, we love, we change, but beneath it all, the same invisible connection hums. Even time seems to participate in this unity. The atoms in your body were once inside stars. The carbon in your bones was cooked in their burning hearts, released in their deaths, scattered across the galaxy, and gathered again here, in you. The calcium in your teeth was born in supernovae. The iron in your blood carries the memory of explosions billions of years old. Entanglement is not just between two particles in a lab, It is written into the lineage of matter itself. When you touch your hand to your heart and feel its rhythm, that pulse is an echo of the cosmic beat. The flow of energy through your cells is part of the same choreography that drives the expansion of galaxies. In a way, consciousness itself is how the universe listens to its own heartbeat. Some physicists have wondered whether this connection extends even further, whether the principles of quantum entanglement might someday help us understand awareness. Not in the mystical sense that thoughts travel across space, but in the poetic sense that every mind, every pattern of perception, is another way the universe observes itself. Perhaps that's what consciousness is, the cosmos folding inward for a moment to witness its own reflection. You don't have to believe that literally to find comfort in it. It's enough to recognize that when you look at the stars, you're not an outsider peering in. You're part of the very system you're observing, made from the same dust, guided by the same rules, woven into the same song. Your gaze completes the circuit. This unity does not erase individuality. A wave in the ocean still has its own form, its own beauty, even though it belongs to the sea. The wave may rise, curl and fade, but its existence adds something unique to the whole. The same is true of us. We are waves of consciousness rising out of the larger ocean of reality. We appear separate, but the separation is only temporary, a pattern formed for a while in the motion of something endless. And in that light, loneliness itself begins to soften. The universe is not an empty stage with a single spotlight on you. It is a vast network of resonance, where every thought, every sound, every particle participates. The air that carries your breath is the same air that whispers across the wings of distant birds. The photons that warm your skin once left the surface of the sun 8 minutes ago, crossing 90 million miles of space just to find you. We are, all of us, part of that unbroken conversation. Even the notion of death becomes gentler through this lens. When the pattern that is you dissolves, its energy and atoms don't vanish. They return to the field, to the same sea that has always been home. Nothing is truly lost. It only changes form, like a note fading into the harmony of a larger song. Entanglement assures us that no part of the universe ever truly disconnects. It only transforms. When Einstein complained about the spooky nature of quantum connection, he was really expressing a wish for order, for a universe that made rational sense. What he didn't realize, perhaps, was that order is still there, only broader than logic can hold. The universe's way of staying connected doesn't fit neatly into the categories we prefer, cause and effect, here and there, before and after. It is an order of wholeness, of mutual belonging. You might think of it as a single breath expanding and contracting through countless forms. Stars inhale, galaxies exhale, consciousness flickers in between. Everything that exists from light to life is part of that breath. Entanglement is simply the scientific echo of that truth, the discovery that the universe never learned to be alone. And as we drift further, this thought begins to turn inward. If the universe doesn't need separateness, perhaps the boundary between observer and observed isn't so strict either. The next step of our journey will explore that very question. Who or what is truly doing the observing? Is it the mind, the instrument, or the universe itself? In that gentle inquiry, physics begins to touch the edge of philosophy, and the cosmos starts to look back at itself through human eyes. Every story of quantum mechanics eventually circles back to a quiet, stubborn question. Who or what is doing the observing? For all our talk of particles and waves, of collapse and connection, something seems to happen when the universe is looked at. But what counts as a look? Is it a human mind, a camera, a beam of light, or something simpler, the act of interaction itself? This is not a new puzzle. When Niels Bohr and his colleagues first tried to interpret quantum theory, they found themselves caught between philosophy and physics. they realize that the moment of measurement, that delicate instant when possibilities settle into outcomes, depends on something touching something else. A photon hits a mirror, an electron meets a screen, a detector blinks, announcing a choice has been made. But does that interaction require awareness? Or is it simply a natural handshake between systems? No consciousness needed, just cause meeting effect. Imagine you're watching rain fall on a window. Each drop that lands changes the reflection slightly, bending the light that reaches your eyes. The world outside doesn't wait for you to notice, it changes regardless. In the same way, physicists have found that even without a human observer, the quantum world behaves as though it knows when an interaction occurs. Detectors alone, unthinking and unfeeling, can turn a cloud of probabilities into a single outcome. Awareness isn't required for the physics to work, and yet, awareness adds something remarkable. It gives meaning to the outcome. The rain might fall whether or not anyone's watching, but only when you look do you see how the droplets form patterns, how each one refracts a different piece of the world. The act of seeing doesn't make the event happen, but it completes the experience. Measurement turns possibility into data. Consciousness turns data into wonder. This difference between observing and witnessing is subtle but profound. A detector observes, a mind witnesses. The universe can operate perfectly well without witnesses, but the presence of awareness transforms mere happenings into stories. We, the observers, bring narrative to nature. When we record the dance of electrons or the fall of stars, we are not outside the experiment. We are the part of the cosmos that notices itself. That idea can feel both humbling and empowering. It suggests that our minds are not separate from the system we study. Every observation we make is part of a two-way relationship. The photons that let you read this sentence are being absorbed by the receptors in your eyes, which in turn trigger signals in your brain. An endless loop of exchange between observer and observed. The boundaries blur. The universe looks at itself through you. Physicists describe this process with careful, neutral words: interaction, entanglement, collapse. But when we translate those words softly, they tell a story of intimacy. Every measurement is a touch, a brief meeting where two parts of reality recognize each other. Even the smallest event, like a photon brushing against a mirror, is a conversation between worlds. To understand this better, imagine two mirrors facing each other. Between them, reflections multiply endlessly, each image slightly fainter than the last. You stand somewhere in the middle, your own reflection repeating into infinity. That's what observation is like. Every act of measurement creates reflections of reality within reality, layers of knowing that stretch outward without end. The deeper you look, the more reflections appear. Some scientists try to separate the human observer from the process entirely, to say that consciousness is just another physical system, no different from a detector. But others have argued that while physics can describe what happens, it cannot describe what it feels like to notice. There's no equation for wonder, no formula for awe. Somewhere between the blinking detector and the human heartbeat lies the quiet bridge between measurement and meaning. When you look at a star, the light entering your eye has travelled for centuries to reach you. That light was emitted long before you were born, long before your planet took its current shape. In a sense, by observing it now, you're completing a story that began ages ago. The measurement, the photon meeting your retina, may be simple, but the awareness that follows it stretches across time. The universe waited billions of years for that moment of contact. Perhaps that's what it means for the cosmos to be self-aware. Not that it thinks or plans, but that it produces beings capable of seeing. Awareness might be its way of reflecting on itself. You, as a conscious observer, are part of that reflection. You're made of the same matter you study, listening to the same rules you describe. It's easy to forget that science, for all its precision, begins in wonder. Every question we ask is an act of curiosity, a reaching out, a small version of that cosmic interaction. When you watch a falling leaf and wonder how it drifts, or when you gaze at the night sky and ask how far the stars go, you're enacting the same pattern as the quantum world: exchange, response, transformation. We could say then that the observer's role is not to control the universe, but to participate in its unfolding. Reality doesn't wait for us to grant it meaning. It simply includes us in the process of creating it. Whether or not consciousness changes the math, it changes the experience. And maybe that's enough. Some thinkers have suggested that the universe might operate like a grand information system, processing interactions as exchanges of data. In that view, everything that happens, every collision, every photon, every thought, is a piece of information woven into an ever-growing tapestry. The observer, then, is not separate from the data, but part of the language through which the universe speaks. We'll explore that idea soon, but for now, it's enough to rest in this gentle truth. To observe is to belong. The moment you look, you're participating in the oldest act of creation, the act of noticing. The atoms that make you were once unobserved, wandering through space for eons until life emerged to give them voice. Awareness doesn't stand outside of nature. It is nature recognizing itself. So the next time you look at something familiar, the curve of a cup, the flicker of a candle, the breath leaving your body, remember that you are not a separate witness to the world. You are the world quietly watching itself. And as we follow this thread a little further, we'll step into that emerging idea that perhaps the universe doesn't run on matter or energy alone, but on something more abstract and delicate: information. We'll ask, not as engineers, but as dreamers, whether the cosmos might be written in a language we're only beginning to understand. Imagine waking up in a dark room, surrounded by soft murmurs of sound. You can't see anything yet, only the faint vibration of voices, like distant whispers through a wall. Slowly, your mind begins to piece them together to make sense of what you're hearing. It's not the words themselves that matter at first, but the rhythm, the rise and fall, the spaces between. In that moment, understanding begins not with light or matter, but with information. Physicists have started to wonder if the entire universe works in much the same way, not as a collection of solid things, but as a flowing conversation of information. Each particle, each field, each interaction could be seen as a bit of a cosmic language, a message written in the grammar of reality. In this view, matter is what happens when information becomes tangible, when data takes physical form. Energy is simply information in motion, the universe talking to itself through patterns of change. This idea began quietly, like a secret hidden in plain sight. In the mid-20th century, when computers were still new and data was counted in punched cards, scientists started noticing something profound. The equations that described how information behaves looked eerily similar to those that described how energy moves. The two were not opposites, but reflections. Information wasn't just a description of reality, it might be reality. Claude Shannon, one of the pioneers of information theory, once defined information as the resolution of uncertainty. It's the moment when something unknown becomes known, when a question collapses into an answer. In that sense, every measurement in quantum mechanics is an act of information exchange. The wave of possibilities narrows, the universe makes a choice, and a new piece of knowledge enters existence. Reality, then, could be thought of as a constant process of self-updating, the cosmos learning about itself, one interaction at a time. You can picture it like a vast, shimmering web made of light, each strand vibrating with bits of data. A photon meeting an atom binding with another, a planet tugging at its star. Every vibration encodes something about the system: position, motion, connection. But unlike digital computers that use zeros and ones, nature's code is analog, fluid, continuous. The letters of this cosmic alphabet aren't written in ink or electricity. They're written in relationships, how things influence one another. In this way, reality becomes less about objects and more about verbs. The universe isn't a thing, it's a happening. Everything exists because it participates in exchange of energy, of information, of meaning. You and I too are made of that same informational rhythm. Every thought, every heartbeat, every memory is a pattern of signals travelling through the matter of our bodies, echoing the same processes that drive galaxies and stars. Some physicists have taken this idea further, proposing what they call quantum information theory. It's a framework where the quantum state, that strange probabilistic wave of possibility, isn't just a physical description, but a storage of information about what could happen. When a measurement occurs, that information changes form, translating potential into history. You could say the universe writes its autobiography through these endless transformations. Others take a more skeptical stance. They remind us that information always needs a medium, something to carry it, like light or matter, and so calling information fundamental may just replace one mystery with another. They ask gently, information about what? Because information, in ordinary language, implies someone who knows it. Does that mean the universe knows itself? Or are we simply using poetic language to describe equations? But even these questions carry beauty. They remind us that science, at its best, dances between precision and imagination. The idea of the universe as information doesn't replace physics. It translates it into something more personal. It allows us to see every particle as a note in a grand cosmic conversation. The laws of nature become syntax. Entropy, the gradual fading of order, becomes the universe's way of rewriting its sentences. You can feel this idea if you close your eyes and listen to the hum of your surroundings, the faint sound of the world moving. Every vibration, every whisper carries information. The room you sit in right now is full of invisible waves. Radio, light, heat, each one carrying messages across time and space. Even the air between your hands is alive with signals, not words, but the quiet presence of shared structure. The world is always speaking. We're only beginning to learn how to listen. Some thinkers, like the physicist John Wheeler, tried to express this truth in a single phrase: it from bit. He meant that everything we call it, every object, every particle, every event, might ultimately arise from bits, from simple yes or no decisions at the foundation of reality. Not digital ones and zeros, of course, but fundamental choices. A photon is here, not there. A spin points up, not down. Each of those choices becomes a word in the universe's ongoing story. But even Wheeler spoke softly about this idea. He didn't claim that reality was literally a computer. He meant something gentler. That information is the way we connect knowledge to existence, the way the universe ensures coherence. Each choice creates a kind of memory, and those memories stack, one upon another, forming the shape of time itself. If we let that sink in, it begins to change how we see everything. The stars are no longer distant lights. They're archives of information, each photon a messenger carrying news of where it came from. The earth beneath your feet is a record of ancient conversations between heat, pressure, and time. Your body, too, is a library of messages written in the language of DNA, which itself is a form of stored quantum information, coiled like poetry within every cell. And yet, the most moving part of this idea is how it brings simplicity to enormity. The universe doesn't need to think to communicate. It doesn't need to plan to remember. Information is its way of staying whole, of keeping the story continuous even as the details change. It's not cold data, but the pulse of relationship. Somewhere in that picture lies the boundary between physics and philosophy, between experiment and reflection. If everything is information, then maybe consciousness is simply another way that information organizes itself, the universe folding inward to experience its own structure from the inside. Or maybe it's the opposite. Maybe consciousness is what allows information to exist at all, by noticing it, shaping it, naming it. We don't yet know which is true, but in a way that's fitting. The universe, if it really is a web of information, thrives on uncertainty. It is built to transform not knowing into knowing, one observation at a time. Every unanswered question is part of the pattern, a gap waiting to be filled, a space where new understanding will soon ripple through. As we drift further, our next step will touch one of the most daring questions of all. Could consciousness itself, the most intimate mystery we know, be linked to these same quantum processes? Could the flicker of thought, the shimmer of awareness behind your eyes, share a rhythm with the trembling of particles? Some have wondered, softly and bravely, if the mind itself might be a quantum phenomenon, a place where the universe dreams about itself. Close your eyes for a moment and imagine the faint pulse behind your thoughts, the shimmer that feels like you. It's not something you can see or hold. It isn't shaped like the neurons it depends on, or the electrical signals flowing through them. It's softer, more elusive, like a glow that exists between moments. Scientists call it consciousness, but that word, neat as it sounds, hides more mystery than it explains. We live inside it, we build our lives from it, and yet we still don't know where it comes from, or how it arises from matter that, on its own, seems lifeless and quiet. For decades, physicists and philosophers alike have wondered whether the secret of consciousness might be found in the same place as the secrets of the quantum world. After all, both are strange, both resist clear definition, and both blur the line between what is and what is experienced. The idea, whispered more than declared, is that the human mind might not be entirely classical, that somewhere within its silent depths thought might tremble with the same uncertainty that rules the atoms. It's a beautiful and dangerous idea. Beautiful because it offers unity. The thought that the same physics that guides stars could also cradle awareness. Dangerous because it tempts us toward speculation, toward building castles of imagination on foundations of fog. So it's important to move gently here, with curiosity but also humility. The notion that consciousness and quantum mechanics might be linked goes back to the mid-20th century. Some thinkers suggested that the mysterious collapse of the wave of possibilities might depend, in some subtle way, on awareness itself. When you look at something, your observation resolves uncertainty. So, could consciousness be the final step in that process? Could the universe, in some sense, require awareness to make choices real? For most physicists, the answer is no. Measurement doesn't need a mind, only interaction. But the question lingers, like a small light in the corner of the room that refuses to go out. It lingers because we still don't know what consciousness is, and because the quantum world keeps reminding us that existence is less mechanical than we once believed. Some scientists, like the physicist Roger Penrose and the anesthesiologist Stuart Hameroff, have tried to give this question structure. They propose something called the orchestrated objective reduction theory, though in our language we might call it the idea that mind and matter share a rhythm. They suggested that the tiny tubes inside brain cells, called microtubules, might sustain delicate quantum states, small waves of possibility, that collapse in coordinated bursts, creating the flashes of awareness we call thought. If true, it would mean that consciousness doesn't merely emerge from the brain, but from the dance of quantum events within it. The idea is elegant, but it remains unproven. The brain is warm, wet, and noisy, a difficult place for fragile quantum coherence to survive. Most physicists believe that any such states would vanish too quickly to matter, yet a few researchers continue to explore the possibility that evolution might have found a way to protect them, that life, being the great organizer it is, could maintain these subtle quantum rhythms. There's another idea, quieter but equally intriguing, known as integrated information theory. It doesn't rely on quantum mechanics at all, but shares its spirit. It says that consciousness arises wherever information is deeply interconnected, when a system is not just complex but unified, so that every part influences every other. In that sense, a conscious system is one that feels itself as a whole. If we look at this softly, it almost sounds like the language of entanglement, connection creating awareness. Whether these models turn out to be right or wrong may matter less than the question they ask. Could awareness be a natural feature of the universe, the way light or gravity is? Could it be that consciousness isn't an afterthought of evolution, but one of the universe's ways of knowing itself? You can sense the poetry in that, even if the science is still uncertain. We often imagine consciousness as something private, something locked inside the skull. But what if it's more like a field, one that touches and responds, shaped by the flow of matter but not confined by it? The mind could then be seen as a kind of local resonance, a standing wave in the vast sea of the cosmos. Your thoughts would be eddies in that current, temporary yet part of something immeasurably large. Of course, these are metaphors, not equations. The danger of talking about quantum consciousness is that it's easy to slip into wishful thinking, to mistake mystery for magic. The real gift of these ideas is not that they give final answers, but that they keep the question alive. They remind us that we are participants in a story too vast to measure, that the line between observer and observed is not a wall but a veil, thin as breath. If the universe truly runs on information, as we explored earlier, then consciousness might be its way of reflecting that information back on itself, a feedback loop of awareness. Every sensation, every act of noticing could be seen as the cosmos momentarily recognizing its own structure. That doesn't make us gods or accidents, it makes us mirrors. The light of awareness is the universe seeing itself, briefly and beautifully through human eyes. And what if consciousness and quantum physics share something even simpler? A comfort with uncertainty? Both refuse to stay within the boundaries we draw. Both thrive on potential, on fluidity, on the coexistence of many possibilities. To be conscious is to live in constant superposition, balancing memory and imagination, presence and absence, thought and feeling. You are always many versions of yourself, folded into one being. Perhaps that, in itself, is the most quantum truth of all. The mind, then, might not be a machine but a melody, one that arises when matter begins to listen to itself. It doesn't need to be mysterious to be miraculous. The simple fact that atoms can arrange themselves into something that wonders about atoms is already one of nature's most astonishing achievements. So, whether or not the mind is truly quantum, its existence is still a cosmic echo, the universe whispering its own story in a new voice. And maybe that's enough. The mystery doesn't need to end for it to be meaningful. As we move toward the final stretch of our journey, the path grows quieter. We've travelled from superposition to consciousness, from particles to perception. Now it's time to rest in reflection, to look back on everything we've discovered and ask what it tells us about being alive in such a delicate, uncertain, and deeply connected universe. The next part of our journey will become a meditation on meaning, on humility, and on the simple beauty of not needing all the answers. There's a quiet honesty in the way science listens to the universe. It doesn't begin with beliefs or expectations. It doesn't demand that reality behave itself or fit neatly into what we think is possible. It simply asks what is true, and then waits patiently for the answer. When you strip away the math, the machines, and the long nights in laboratories, physics is really an act of humility. It starts not with certainty, but with curiosity. A question is posed, an experiment is built, and the universe responds, sometimes in whispers, sometimes in thunder. The results aren't always what we hoped for, but they are always what is. There's a phrase that captures this spirit perfectly. Physics isn't troubled by reality being bizarre, only we are. The equations don't flinch at quantum weirdness, or at particles that seem to be in two places at once. They simply describe what happens. It's our minds that struggle, our need for order that trembles when the world refuses to play by familiar rules. We humans like to think of ourselves as rational creatures, but what we often crave is not truth, it's control. We want the world to make sense because that feels safe. We build patterns, routines, and stories around what we can predict. And yet, quantum mechanics quietly reminds us that not everything is predictable, that the universe has a streak of independence. It behaves the way it must, not the way we wish. That realization can feel uncomfortable at first. But there's peace hidden inside it, like calm water beneath a storm. When you stop expecting the world to fit your expectations, you start to see it as it truly is. Vast, surprising, alive with possibility. The unknown ceases to be an enemy. It becomes a companion, a teacher. Think of a leaf floating down a stream. The leaf doesn't try to control the current. It doesn't resist the turns or the eddies. It drifts, responding to the water beneath it. In the same way, physics teaches us to drift with the truth rather than fight it, to let reality carry us, even when the current bends toward the unfamiliar. The early pioneers of quantum theory had to learn that lesson in real time. Every discovery they made contradicted something they had once believed. Light behaved like a wave, then like a particle, and then somehow both. Time and space, once thought absolute, began to bend and stretch. Even observation itself, something as simple as looking, turned out to shape the outcomes of experiments. They could have rejected these findings, but they didn't. Instead, they listened. They let go of what they thought the world should be and allowed the evidence to guide them. That act of surrender wasn't weakness, it was courage. To look at something that defies your understanding and still say, "Yes, I accept." You is one of the most human acts imaginable. There's something deeply comforting about that. It means we don't have to have all the answers to participate in truth. We only need honesty, the willingness to look, to ask, and to listen. In your own life, you've probably felt echoes of this. You plan for one outcome, and something unexpected happens instead. A conversation takes a turn you didn't foresee. A door closes, and another, entirely unplanned, opens. At first, you resist, wanting to pull things back to the version of reality you imagined. But if you let go, even a little, something shifts. You begin to notice patterns you couldn't see before, small harmonies hidden inside the chaos. The universe works like that too. It doesn't promise simplicity, it promises coherence. Everything that happens, no matter how strange, fits somewhere in the larger pattern. We may not always see that pattern clearly, but it's there, in the orbits of planets, in the decay of atoms, in the rhythm of breath. Physics without prejudice means letting go of the need for the universe to comfort us. It means finding comfort instead in its honesty. The equations don't tell us what we want to hear. They tell us what's there. And that truth, even when strange, is a kind of beauty. It's easy to forget that science, at its core, isn't about conquering nature. It's about conversation. Every experiment is a question and every result an answer. Sometimes the answers are gentle. Sometimes they upend everything we thought we knew. But reality never lies. When you stand beneath the night sky, looking up at stars that burned billions of years before you were born, remember, they're not waiting for your approval. They simply are. And yet, by seeing them, by wondering about them, you become part of their story. The act of looking connects you to their light. The photons that left their surfaces before human civilization began are ending their journey in your eyes tonight. That's physics too. Connection without demand. In that sense, to let go of certainty is to make room for belonging. When we stop insisting that reality fit our design, we start to feel how deeply we are part of it. Every atom in your body follows the same laws as the stars. Every breath you take obeys the same thermodynamic principles that govern galaxies. There's a quiet democracy to existence. No particle more important than another. No rule bent for convenience. You might think of it like music. When an orchestra plays, no single instrument controls the piece. The harmony arises from cooperation, not domination. Each note has its place, and the beauty comes from listening, not forcing. Physics without prejudice is the art of that listening. The willingness to let the universe play its tune, even when we don't know the melody. And perhaps, if we listen closely enough, we'll realize that the unpredictability we fear is actually what makes life vivid. Certainty is stillness, but uncertainty is movement, the constant unfolding of possibility. The quantum world, with all its strange behaviors, isn't a rebellion against reason. It's reason's most honest expression. It says, "I will not pretend to be simple just to make you comfortable." If we could adopt even a fraction of that honesty in our own lives, how different the world might feel. We would learn to meet the unknown not with anxiety, but with curiosity. We'd replace control with participation, resistance with grace. So as you breathe softly and let your thoughts settle, imagine yourself as that leaf again, floating down the stream of reality. The water carries you through turns you cannot see, but you are always moving toward understanding. You don't need to steer, you only need to notice. And from that stillness, we can begin to see another truth, that even in disagreement, the universe remains harmonious. Different minds, different theories, different interpretations can all describe the same reality from different angles. The next part of our journey will explore that harmony, the way beauty and logic intertwine, the way truth can sing in more than one voice. Imagine walking into a grand concert hall just as the orchestra begins to tune. You hear a chaos of sound at first, strings warming, woodwinds breathing, percussion murmuring in the distance. Then slowly, as the conductor raises a hand, the chaos settles into harmony. Each instrument keeps its own voice, its own texture, yet all are joined in one unfolding melody. Physics, in its quietest moments, feels very much like that, a gathering of truths that may sound different, yet all describe the same underlying song. Quantum mechanics is the perfect example. Its equations are universal, their predictions precise and consistent. But the stories we tell to interpret those equations, the ways we imagine what the math means, vary wildly. Some scientists prefer the Copenhagen interpretation, finding beauty in its humility, the acceptance that the world becomes specific only when observed. Others prefer the many worlds view, drawn to the grandeur of infinite branches of possibility. Still others hold to Bohm's vision, seeing in it the comfort of hidden order. None of these interpretations are wrong, and none are fully proven right. They are different instruments playing the same symphony, each offering a distinct timbre to the same underlying melody. In the end, these choices are often aesthetic rather than empirical. They reflect the sensibilities of the listener. One physicist values simplicity and embraces the Copenhagen calm. Another craves completeness and finds peace in Everett's branching multiverse. What this tells us is that even in the realm of pure science, beauty still guides us. Our theories are not only descriptions of reality, they're expressions of taste, shaped by the same instinct that makes us prefer one colour, one sound, one scent over another. It's easy to think of physics as dry, but at its heart lies an emotional core, a love for coherence, symmetry, and rhythm. The equations themselves, stripped of metaphor, are full of elegance. They whisper of balance, of forces that mirror each other, of probabilities that sum to unity, of patterns that repeat across scales from quarks to galaxies. Many physicists have confessed in quieter moments that they follow beauty as much as logic. When a new equation feels beautiful, when it fits the rhythm of nature like a perfectly resolved chord, it often turns out to be true. There's something deeply human about that. We don't just want the universe to be correct, we want it to be graceful. We hope that its laws aren't merely functional, but harmonious, that the cosmos isn't an accident of chaos, but a kind of art. If we translate the language of equations into imagery, we might picture the universe as a vast painting in motion. Every brushstroke of light, every contour of matter, contributes to a composition that's constantly being revised. The beauty lies not in static perfection, but in dynamic balance. Galaxies swirl like spirals of colour, subatomic particles shimmer like the finest grain of texture. To see the whole, you must step back, not to analyse, but to feel. And yet, within that harmony, there's room for difference. Just as music gains richness from contrast, the low hum of a cello beneath the bright trill of a flute, our interpretations of the universe enrich each other through diversity. Copenhagen offers humility, Many Worlds offers awe, Bohm offers unity. Together they create a fuller emotional landscape, a way to experience science not as certainty but as conversation. Perhaps that's the real message of the aesthetic universe. Truth can wear many faces without losing its essence. When light behaves both as a wave and as a particle, it isn't betraying logic. It's revealing that logic can have texture. The quantum world refuses to flatten itself into a single definition, because reality itself is richer than simplicity allows. We live our lives the same way. You can describe yourself as a mind or as a body, or as a collection of memories, and each description would be true but incomplete. You're not one story but a symphony of overlapping interpretations. The same is true for the universe. It doesn't require us to pick a favourite version, it invites us to listen to them all. There's a quiet lesson in that, especially for a world so quick to demand certainty. We often divide knowledge into categories: science versus art, logic versus emotion, reality versus imagination. But the deeper you go, the more those divisions blur. Science is full of poetry, art is full of structure, logic itself is beautiful. What matters is not which lens you choose, but how clearly you can see through it. When you think about it, the laws of physics are not that different from the laws of music. Both describe relationships. In music, it's the relationship between notes. In physics, between particles or fields. In both, beauty arises from proportion, rhythm, and balance. A melody too repetitive becomes dull. One too chaotic becomes noise. Nature walks that line with infinite grace. From the heartbeat of an atom to the orbits of planets, everything vibrates in tune with everything else. If you've ever felt awe looking at a sunset, or peace watching ripples spread across a pond, that feeling is the aesthetic sense at work, the recognition of harmony between complexity and simplicity. Physics, at its best, evokes that same feeling. Its equations are ripples on the pond of understanding, mathematical reflections of something profoundly serene beneath the surface. Some thinkers have even suggested that beauty itself may be a clue to truth. When theories are elegant, when they fit nature with minimal strain, they often reveal something fundamental. Einstein once said, "The most incomprehensible thing about the universe is that it is comprehensible." Perhaps what he meant was that the universe doesn't just allow understanding, it invites it. It seems to want to be known, as if revealing its beauty were part of its design. So when scientists debate interpretations, when one finds peace in probabilities and another in hidden waves, and it isn't conflict, it's polyphony. It's the sound of many voices exploring the same vast room, each echo helping us understand its shape. Maybe that's what makes the universe aesthetic. Not that it's pretty or polished, but that it supports endless ways of being seen. Its truth is resilient enough to accommodate wonder. It doesn't collapse under scrutiny, it sings back. And when you listen closely, the differences between theories start to matter less. What remains is the shared awe of discovery, the recognition that we're all standing in the same concert hall, listening to the same great symphony, each hearing it from a slightly different seat. So take a moment, even now, to let that harmony sink in. Whatever interpretation you find most beautiful, it belongs to the same melody of existence. Reality doesn't demand that you choose, it only asks that you listen. And as our quiet journey continues, we'll turn to that act of listening itself, the way we question, the way we hear the universe answer back. For science, in the end, is not about mastering the world. It's about learning to ask softly and to hear the whisper that comes in reply. Imagine standing beside a great still lake at dawn. You toss a pebble into the water and watch the ripples spread, widening until they fade into stillness. The surface answers you softly with a pattern, circles expanding outward as though the lake was speaking in its own quiet language. Science is like that. Every experiment we make is a pebble we drop into the water of reality, and every observation is a ripple, the universe's response to our question. It's easy to think of science as a list of facts, but at its heart, it's a form of conversation. We ask, and the world answers, not always clearly, not always as we expect, but always truthfully. Each question we pose is a kind of touch, a gentle knock on the glass of the unknown. And when the universe replies, it does so in the only way it can, through motion, through pattern, through change. Think of the first scientists who wondered what fire was. They couldn't explain it with equations or models. They simply observed, listened, and took note of its rhythms, how it consumed, how it danced, how it gave both warmth and light. That attention, that willingness to listen without judgment, was the beginning of understanding. Every discovery since then has been another version of that same moment. The quantum world makes this conversation subtler, more dreamlike. When we measure something, the spin of a particle, the direction of a photon, we're not just asking, "What are you?" We're also asking, "How will you answer me this time?" Because in the quantum realm, answers aren't fixed. They depend on the question, on the way we ask, on the tools we use to listen. The act of questioning becomes part of the story. This is what makes physics so deeply human. For all its precision, it mirrors our own way of learning about life. We ask the world questions and the world answers in its own dialect. We ask, "What is love?" And life replies with laughter and heartbreak. We ask, "What is beauty?" And the universe gives us sunsets, equations, and music. All different, all true. The conversation never ends, it only deepens. Every experiment is a moment of curiosity meeting existence. Even the most complex machines, particle accelerators, the space telescopes, are, in essence, instruments of listening. The detectors don't shout into the void, they wait, patiently, for the faintest reply. A single photon, a shift in frequency, a vibration too small to see. Each one a syllable in the universe's endless story. And sometimes the answers come not as clarity, but as mystery. When we built the first quantum experiments, we expected the universe to behave like a polite student, consistent, obedient, easily explained. Instead, it gave us paradoxes and puzzles, particles that behaved like waves, outcomes that changed when observed, correlations that stretched across space. The universe didn't give us neat solutions, it gave us poetry. That can be unsettling, but it's also generous. Because each new mystery opens another question. Every strange result is a new invitation to look closer, to listen more carefully. The conversation between humans and nature has no final word. It's a dialogue that deepens with time, just like any friendship. You might think of it this way. When we ask, "What is the universe made of?" we're really asking, who are we in relation to it? The answers we find, from atoms to galaxies, from uncertainty to entanglement, change how we see ourselves. We're not separate from the world we study. We're one of its questions, learning to speak its language. There's an old saying in physics: the universe is under no obligation to make sense to us. But perhaps it already does, just not in the way we expect. Maybe it speaks in rhythm instead of words, in patterns instead of sentences. When a scientist studies quantum interference, waves overlapping and cancelling each other, it's not so different from listening to harmony in music. When an astronomer tracks the orbit of a star, it's a kind of choreography. The universe is always speaking, we're just learning to recognise its accent. If you could step back and listen to all of it at once, the spin of electrons, the roar of black holes, the heartbeat of living things, you might hear a single, slow melody. A conversation without beginning or end, woven from motion and light. Every act of science, every spark of curiosity adds another note to that melody. And what makes this conversation so moving is that it's mutual. The universe doesn't change just because we look at it, or maybe it does, a little. When you touch something, however lightly, it touches you back. When you look at a star, its light enters your eyes, becomes part of your mind. The act of observing connects you to the thing observed. You can't ask a question without becoming part of the answer. That's the quiet paradox at the heart of all discovery. The more we learn about the universe, the more it learns about itself through us. Our questions are its reflections. Our curiosity is its echo. The cosmos doesn't speak with words, but with existence. Its language is form, motion, and transformation. We're fluent only in fragments of that language, yet even fragments are enough to feel the beauty of the whole. And maybe that's why so many scientists, after years of calculation and observation, end up sounding like poets. The deeper they go into the workings of nature, the more they find themselves speaking of wonder, of symmetry, elegance, inevitability. When you strip the numbers away, what remains is a sense of awe, not fear, not confusion, but reverence. The unknown isn't hostile, it's just quiet. It waits patiently for us to ask better questions. Each time we do, it responds, not always with clarity, but always with truth. Sometimes that truth takes the shape of light. Sometimes it takes the shape of silence. Both are answers worth listening to. So tonight, as your thoughts slow and your breath evens, imagine that you're standing beside that still lake again. The stars above are questions you haven't yet asked. The ripples across the water are the universe replying softly in its timeless rhythm. You don't have to understand the language to feel its meaning. You only have to listen. And as we drift deeper into that silence, our journey will draw to a close, not with an answer, but with peace. Because the greatest gift of all these questions is not knowledge, but connection. In asking, we've learned that we were never separate from the universe at all. Somewhere in the soft space between thought and sleep, a question lingers, not one to be answered, but one to be felt. It asks, what does it mean that we exist at all? Out of all the ways atoms could have arranged themselves, they formed you, a being capable of wondering, capable of asking the universe to explain itself, even as you float within it. That's where every journey through science eventually leads, not to a final equation, but a quiet wonder at the fact that anything exists, and that we have the privilege of knowing it does. Quantum mechanics didn't make the world strange. It simply revealed the strangeness that was always there, waiting under the surface of what we thought we understood. We once imagined that the universe was a tidy machine, each gear clicking in perfect sequence, predictable and self-contained. But as we looked closer, the gears dissolved into waves, and the waves dissolved into probabilities, and the probabilities dissolved into a shimmering question mark that whispered, reality is larger than you think. It's easy to feel lost in that vastness. But if you listen closely, there's comfort in it too. Because what quantum physics really tells us is that the universe is participatory. It's not a cold stage on which life happens by accident. It's an unfolding story that includes us, our thoughts, our questions, our small acts of observation. When we look at the stars, we're not separate from them. We are part of the same dance of light and matter, the same exchange of energy that has been happening since the beginning of time. Remember the magic box from the beginning of our journey, the box that held a mystery until you dared to look inside. Maybe reality itself is still that box. Maybe the universe is still choosing softly, moment by moment, what to reveal. Each breath, each observation, each act of awareness opens another lid. The story continues, always half-written, always inviting you to look a little further. There's something profoundly gentle about that thought, that existence isn't finished, that creation is still happening in every instant. The universe is not a completed painting hanging on a gallery wall. It's a canvas that's still being brushed with a light. And in some small way, every time you notice something, a raindrop trembling on a leaf, the pulse in your wrist, the glow of dawn through a window, you're participating in that art. You're both the viewer and the stroke of the brush. Maybe that's the quiet lesson quantum mechanics has been trying to teach us all along. That being is not about certainty, but about becoming. The world isn't fixed, it's alive, endlessly rearranging itself into new combinations, new possibilities. The particles that make you are not things, they are events, processes in motion, small moments of the universe experiencing itself. You too are an event, a pattern that breathes, changes and wonders before merging back into the larger flow. If that sounds abstract, think of the sea. Every wave has its own shape, its own rise and fall, but none of them are separate from the ocean. Each one exists only because the sea moves through it. When the wave crashes and disappears, the ocean remains. You're like that, a wave on the surface of the cosmic ocean, temporary but real, distinct yet inseparable from the water that forms you. And just as the sea never resents the passing of its waves, the universe never loses what it creates. The energy of your existence, your experiences, your thoughts, all become part of the ongoing rhythm of everything. When you rest, when your body quiets and your mind drifts toward dreams, you're not stepping away from the universe, you're falling back into it. This is what physics, when spoken softly, really says. Everything is continuous. The distinction between the observer and the observed, between the question and the answer, fades like twilight blending into night. What remains is a unity so complete that it can only be described in metaphors, a conversation where speaker and listener are the same, a song where the note and the silence belong to each other. You might wonder then what it means to live inside such a mystery. Perhaps it means learning to rest in not knowing, to find peace in the questions themselves. Certainty can be comforting, but it's also a cage. Wonder, on the other hand, keeps the world open. It lets the universe stay alive, unfinished, full of movement. That's the gift of science at its most human level. Not just discovery, but awe. The understanding that truth is not a possession, but a relationship. Every fact we learn, every experiment we build is a form of listening. And what we hear, again and again, is that the cosmos doesn't end at the edges of our perception. It keeps unfolding, gently, like a horizon that recedes as you approach it. So here, at the end of our quiet exploration, you can let the questions rest. You don't need to solve them. They've already done their work by leading you here, to stillness, to gratitude, to the awareness that you belong to something immeasurably vast and exquisitely delicate. The same quantum laws that govern the flicker of distant galaxies also guide the rhythm of your breath. You are, in every measurable way, made of the same light you gaze upon. Maybe that's what reality really means. not a collection of facts, but a shared story of presence, a universe that remembers itself through you and you through it, a pattern of observation, curiosity, and love. And now, whether your eyes are still open or already drifting closed, know this. The universe continues its silent conversation. The stars keep whispering across space. The particles that once danced in the hearts of ancient suns still shimmer in your blood. You're not outside the mystery. You're the mystery, resting for a moment before beginning again. So breathe softly and let yourself dissolve into that quiet. The same wave that brought you here will carry you onward, through thought, through dream, through the dark and gentle sea of being. And as you drift, remember, even in the silence, the universe hums with possibility. You are part of that hum. You always have been. You always will be. Thank you for journeying through this story. Sleep peacefully wherever you are, beneath the same vast sky that gave you life and still holds you quietly in its light.